The universe holds secrets that defy every law we think we know. We are about to journey through 35 of the most baffling space anomalies ever recorded, cosmic riddles that have stumped our greatest scientists for decades and sometimes centuries. By the end, you will understand just how strange, vast, and humbling reality truly is. We will encounter a signal so provocative an astronomer scrawled "wow" in the margin, and a star that dims as if something colossal is blocking its light. What does it feel like to stare into an abyss of perfect cosmic silence? It was a single, brilliant spike on a roll of paper that changed everything. On the night of August 15, 1977, the Big Ear radio telescope in Ohio was quietly listening to the stars, its data printing out line after line of numbers and letters representing the faint whispers of the cosmos. Then, for exactly 72 seconds, the silence was shattered. The signal was not a natural cosmic hiss. It was a focused, powerful burst of radio waves, a perfect narrowband transmission that rose and fell in intensity exactly as you would expect if a distant source passed through the stationary telescope's field of view. It came from the direction of the constellation Sagittarius, and it used a very specific frequency, 1420 MHz. This is the natural emission frequency of hydrogen, the most common element in the universe. Scientists have long theorized that any advanced civilization wanting to announce its presence might use this universal landmark as a cosmic lighthouse, a channel everyone would know to monitor. When astronomer Jerry Amon was reviewing the data printout days later, he saw the alphanumeric sequence representing the signal's incredible strength. He was so stunned he circled the code and simply wrote one word in the red pen's margin: "Wow." The wow signal, as it became forever known, was everything researchers had hoped to find, a candidate so perfect it seemed too good to be true. And then it vanished. For over 4 decades, teams have pointed every available instrument back toward that patch of sky, listening with technology far more sensitive than Big Ear. They have heard nothing but the usual cosmic static. The leading natural explanation suggested it might have been a reflection from a passing human-made satellite or perhaps an emission from a comet, but those theories have largely been debunked or found insufficient. The signal's unique properties and its perfect alignment with the hydrogen line keep it alive as the one that got away, a solitary, enigmatic shout into the void that we happen to be listening at the exact right moment to hear. Was it a fleeting cosmic accident or a beacon from a distant intelligence that simply has not spoken again? Its silence is almost as profound as its brief, roaring message. That solitary red pen mark on a data sheet ignited a fire that still burns today. The wow signal did more than just puzzle astronomers. It fundamentally rewired the entire search for extraterrestrial intelligence. It became the ghost in the machine, the proof of concept that something out there could send a signal so perfectly crafted it felt intentional. In the decades since, we have thrown our most powerful tools at the problem. Projects like the privately funded Breakthrough Listen initiative now scan millions of stars across vast swaths of the radio spectrum, using equipment millions of times more sensitive than the humble Big Ear telescope. They have repeatedly pointed their arrays toward that same quiet corner of Sagittarius, listening with an ear so sharp it could hear a cell phone signal from the nearest star. And they have heard nothing. This profound silence is its own kind of message. If the wow signal was indeed a call from another civilization, why did it never repeat? One compelling theory is that it was not a continuous broadcast aimed at us, but a powerful, directed beacon. Picture a distant lighthouse, its beam sweeping through the galactic dark. Our planet, for those 72 glorious seconds, happened to sail directly through that narrow shaft of light. By the time we turned to look, the beam had already moved on, leaving us in the cosmic shadows once more. This possibility transforms the anomaly from a failed phone call into a tragic near miss, a fleeting moment of contact lost to the immense scales of space and time. Beyond the science, the wow signal embedded itself into our culture. It is the star of documentaries, the subject of countless articles, and a foundational story told to young, aspiring scientists. It represents the tantalizing maybe, the concrete evidence that the question "are we alone?" is not just philosophical but potentially empirical, and that is its ultimate, enduring power. Despite all our technological leaps, with telescopes in space and algorithms sifting through cosmic noise, that one brief blip from 1977, captured on a simple printout, remains the most compelling, the most perfectly crafted candidate for an alien hello we have ever found. It stands alone, a quiet monument to our longing, and a reminder that the universe's greatest secrets may only reveal themselves once. That profound silence from the Sagittarius constellation taught us a hard lesson about cosmic patience. But sometimes the universe does not whisper a single, perfect signal. It throws a tantrum of light that defies every expectation. Enter KIC 8462852, a star so strange it needed a human name, Tabby's star. Found within the Kepler Space Telescope's treasure trove of data, this ordinary-looking star, slightly larger and hotter than our Sun, was doing something extraordinary. It was flickering. Kepler's mission was to find planets by detecting the tiny, regular dips in starlight caused as they transited or passed in front of their host star. A typical dip is minuscule, often less than 1%. Tabby's star did not play by those rules. Its light would plummet by staggering amounts, up to 22%, and these dips were chaotic. They had no regular rhythm, their shapes were jagged and asymmetrical, and they lasted for days or even weeks. A planet, even a gas giant, could never cause such a dramatic blockage. This was not the signature of an orbiting world. It was the shadow of something vast, irregular, and utterly unexplained. The strangeness sparked immediate and electrifying speculation. In a paper, astronomer Tabetha Boyajian and her team laid out every conceivable natural cause, from planetary collisions to swarms of giant comets. Yet one possibility, mentioned almost in passing, captured the public's imagination like wildfire. Could this be evidence of alien engineering on a scale beyond comprehension? The hypothesis pointed to a theoretical concept called a Dyson swarm. Imagine a civilization so advanced it has consumed all the planetary energy in its home system. To power its continued growth, it might build millions of giant solar collectors, placing them in orbit around its star to harvest its immense energy output. Such a colossal, incomplete structure, still under construction, would block starlight in exactly the irregular, deep, and unpredictable patterns Kepler observed. For a moment, the internet held its breath. Had we finally found it, not a radio signal, but the physical footprint of a Type II civilization? Science, of course, demanded more than excitement. Researchers turned every available eye toward Tabby's star, from ground-based observatories to the Hubble Space Telescope. The alien megastructure idea, while thrilling, faced immense scrutiny. The more we looked, the more evidence pointed toward natural, if bizarre, causes. Detailed analysis of the light during these dimming events revealed a crucial clue. The star did not dim equally across all colors of light. It dimmed more in blue light than in red. This is a classic fingerprint of starlight passing through dust, not solid metal or megastructure panels. Dust particles are tiny, and they scatter blue light more effectively, letting redder light pass through. The leading theory now suggests a chaotic, immense cloud of fine dust, perhaps from the breakup of a giant comet or a family of them, is orbiting the star in a highly elliptical path. As this dusty debris passes between us and Tabby's star, it creates those deep, irregular shadows. But just as that explanation began to settle the debate, a deeper layer of the mystery emerged. Long-term studies of the star's brightness over the past century, using old photographic plates, revealed something even more perplexing. Tabby's star is not just dipping erratically, it is also slowly, steadily fading over decades. This long-term dimming trend is separate from the dramatic short-term dips, and it is far harder to explain with simple comet swarms. It suggests something more fundamental might be happening within or around the star itself, perhaps a vast, uneven ring of dust or some form of intrinsic stellar variability we have never seen before. So while the most sensational answer has likely been ruled out, the truth remains elusive. Tabby's star stands as a monument to cosmic complexity, a reminder that nature can conjure phenomena so strange they brush against the edges of science fiction, forcing us to look deeper and question everything we think we know about how stars behave. The fingerprint of dust on the light from Tabby's star was the crucial clue that turned the tide. When astronomers analyzed the starlight during its deepest dimming events, they noticed something specific. The star did not fade uniformly like a simple light bulb being dimmed. Instead, the blue wavelengths of its light were blocked far more dramatically than the red ones. This is a classic telltale sign. Tiny dust particles, much smaller than a grain of sand, are excellent at scattering shorter blue light waves while allowing the longer red waves to pass through more easily. It is the same reason our sunsets appear red and orange, as the blue light is scattered away by dust in our own atmosphere. This wavelength-dependent dimming was the definitive evidence that ruled out solid, monolithic structures like alien megastructures. The shadow passing in front of Tabby's star was not a solid wall of metal or machinery. It was a vast, diffuse, and incredibly opaque cloud of fine cosmic dust. But solving one mystery only opened a far more compelling one. If it is dust, then where on Earth, or rather, where in that star system, did so much of it come from? To dim a star by over 20% requires a staggering amount of material. The leading theory involves a truly catastrophic event, the violent breakup of a massive celestial body. Imagine a planet, or perhaps a moon the size of our own, suffering a colossal collision or being torn apart by the gravitational forces of its star. Such an event would create an expanding, chaotic debris field of billions of fragments, which would then continue to collide and grind themselves down into finer and finer dust. This immense, swirling cloud, trapped in a long, elliptical orbit around the star, would periodically drift between Tabby's star and our telescopes, creating those irregular, deep shadows we observe. The unpredictable nature of the dimming suggests this is not a stable, serene ring like Saturn's. It is a messy, evolving, and violent aftermath, a celestial crime scene where we are witnessing the ongoing consequences. This raises a profound question about our own cosmic neighborhood. Could such apocalyptic events happen here? Our solar system's distant past was likely just as violent, with planets forming and colliding in a chaotic dance. Tabby's star offers us a rare, real-time window into that destructive process, showing us how planetary systems can sometimes tear themselves apart. The star's additional, century-long slow fading adds another layer, hinting that this dust might be spreading into a broader disk, perhaps eventually forming a new generation of planets from the ashes of the old. So while the alien megastructure dream has faded, the reality is, in many ways, more astonishing. Tabby's star is not a monument to alien engineers, but a natural laboratory of cosmic destruction and rebirth. It teaches us that the universe is capable of spectacle on a scale that rivals our wildest science fiction, using only the ordinary tools of gravity, collision, and time. The anomaly pushes us to ask not if aliens are out there, but to wonder what other incredible, natural phenomena we have yet to imagine, waiting in the starlight to challenge our understanding once more. The destruction of worlds around Tabby's star shows us a slow, grinding chaos, but the cosmos also possesses a capacity for sudden, unimaginable violence, a flash of energy so intense it can outshine entire galaxies. These are fast radio bursts, discovered not by a telescope in real time, but by a sharp-eyed graduate student named Duncan Lorimer sifting through old data in 2007. they are the universe's most powerful and mysterious explosions. For just a few milliseconds, a point in the distant darkness unleashes a torrent of radio waves carrying more energy than our Sun produces over 80 years. The first one was so bizarre, so far outside any known category, that scientists spent years checking and rechecking the data, convinced it must be some terrestrial glitch, a microwave oven on the observatory campus, or a satellite's errant signal. But it was real, and it came from far, far beyond the Milky Way. This extragalactic origin is what makes them so staggering. These bursts are not local fireworks. They are cosmic sirens screaming across billions of light years, their signals stretched and weakened by the expansion of the universe itself by the time they reach us. For years, every new detection was a solitary event, a single, brilliant pop in the dark that never happened again. This made them nearly impossible to pin down. How do you study a phenomenon that appears once and then vanishes forever? The leading theories were suitably cataclysmic. Perhaps they were the final death cries of evaporating black holes, or the colossal shockwaves produced when two ultra-dense neutron stars spiraled together and merged in a flash of gravitational waves. Then everything changed. In 2016, astronomers confirmed that one burst, catalogued as FRB 121102, was repeating. It was not a one-time catastrophe. Something was out there, alive, and firing off these monstrous energy shots again and again. This single discovery shattered the leading one-shot models. You cannot have a star die multiple times. Suddenly, the source had to be something that could survive its own outburst, something that could power these bursts repeatedly. The theories scrambled. Attention turned to magnetars, a special type of neutron star with magnetic fields so powerful they could crush atoms. A starquake on such an object, a sudden cracking of its crust under immense magnetic stress, could theoretically produce a burst. But could even a magnetar generate the extreme energies observed from billions of light years away? The debate was fierce. The plot thickened further with the detection of FRB 180916. This repeater did not just fire at random. It followed a cycle, a 16-day period where it would be active for about 4 days and then fall silent for 12. This periodicity was a game-changing clue. It strongly suggested the source was orbiting something, perhaps a companion star. The regular silence could be explained when the object, maybe a magnetar, passed behind a thick cloud of gas or plasma from its partner, blocking the bursts from our view. The hunt was no longer just for a source, but for an entire system, a cosmic engine with moving parts we could barely comprehend. With every new detection, the mystery deepens, pulling us into a frantic chase to understand these celestial lightning bolts that flash and fade before we can even blink. The repeating bursts from FRB 121102 were not just a fluke, they were a cosmic address. For the first time, astronomers could point their most powerful telescopes at the exact patch of sky and ask, what is there? The answer was astonishing. The bursts were traced back not to a brilliant spiral galaxy like our Milky Way, but to a tiny, faint dwarf galaxy over 3 billion light-years away. This galaxy was a cosmic runt, forming new stars at a frantic pace, a turbulent and metal-poor environment. And at its heart, right where the radio bursts were coming from, sat a second persistent mystery, a steady, weaker source of radio waves. This was not the burst itself, but a constant, glowing ember that never went out. The pairing was a crucial clue. It suggested the source of the fast radio burst was not a one-time explosion, but an ongoing engine, a powerful object embedded in a dynamic environment. The leading suspect became the magnetar, the ultimate cosmic powerhouse. Imagine the core of a giant star collapsed into a sphere just 12 miles across, but spinning hundreds of times per second and wrapped in a magnetic field a quadrillion times stronger than Earth. This magnetic field is so unimaginably intense it strains the very fabric of the star itself. Theorists propose that a fast radio burst could be the sound of that star cracking. A starquake, a sudden shift in the magnet's solid crust under unbearable magnetic stress, could release a cataclysmic wave of energy. Alternatively, the magnetic field lines themselves might snap and violently reconnect, a process that on the Sun creates solar flares, but here amplified to a universe-shaking scale. This model of a young, hyperactive magnet in a star-forming dwarf galaxy fit the data beautifully. It explained the repeating nature, the persistent radio source, and the incredible energy. The mystery seemed to be narrowing until our own galactic backyard decided to hand us a gift. In April 2020, monitors picked up an intense double peak of radio waves and X-rays coming from a known object within the Milky Way, a magnet named SGR 1935+2154. This was not a signal from billions of light-years away. It was in our neighborhood, just 30,000 light-years distant. For the first time, we had caught a fast radio burst in the act and could unequivocally name its source a magnet. This was a monumental breakthrough, the smoking gun that proved at least one major class of these bursts came from these magnetic monsters. But instead of solving the puzzle, it deepened it in unexpected ways. The Milky Way's burst was thousands of times weaker than the extragalactic ones. If the same type of object produced both, then the distant ones must be unimaginably more energetic, or we are seeing them through some cosmic lens that amplifies their signal. Furthermore, we now face the engine problem. We know magnetars can do it, but are they the only ones that do? Why does one magnetar fire off repeated bursts for years, while another might only ever produce a single silent pop? The mystery has evolved from simply asking what they are, to asking how their incredible engines work, and what special conditions make some of them shout so loudly we can hear them across the universe. The discovery that magnetars could be the engines of fast radio bursts gave us a profound new tool, a way to listen for the violent tremors of these magnetic monsters. But what if our most fundamental assumptions about the universe's structure were built on a cosmic ingredient that could simply be missing? For decades, dark matter has been the indispensable, invisible scaffolding of our cosmos. We cannot see it, touch it, or detect it directly, but we know it must be there. Its immense gravitational pull is the only thing that explains why galaxies spin as fast as they do without flying apart, and why giant clusters of galaxies hold themselves together. It is the unseen glue binding the visible universe. So what happens when you find a galaxy that seems to have none? In 2018, astronomers studying a faint, ghostly patch of light called NGC 1052DF2 got the shock of their careers. This was an ultra-diffuse galaxy, a wispy, see-through collection of stars so thinly spread you could look right through it to the galaxies beyond. To measure its mass, the team used a classic method. They observed 10 bright globular clusters, dense balls of ancient stars orbiting the galaxy's outskirts. The speed of these clusters is a direct gauge of the galaxy's total gravitational pull. The faster they move, the more mass, including dark matter, must be present to hold them in orbit. The results were unequivocal and utterly baffling. The globular clusters were moving far too slowly. Their leisurely orbital speeds indicated that the gravity holding this galaxy together could be accounted for entirely by the visible mass of its stars. There was no room left for dark matter. This was like finding a towering, stable building constructed without any steel framework, held up by its bricks alone. It directly challenged a cornerstone of modern cosmology, the idea that dark matter and galaxies are inseparable partners, born together and growing as one. The immediate question was how. Could this galaxy have had its dark matter violently stripped away? Perhaps it wandered too close to a massive neighbor, and gravitational tides ripped the invisible halo away, leaving the visible stars behind like a shipwreck's debris. Yet NGC 1052DF2 shows no signs of such a traumatic encounter. Its stars are calm and ancient, with no telltale scars of disruption. Another, more radical possibility is that it never had dark matter to begin with. Maybe it formed in a unique way from gas that was already stripped of dark matter during a chaotic galactic collision, condensing into stars under unusual conditions. This idea suggests a new class of galactic orphan, objects that defy the standard recipe of the universe. And then there is the most profound challenge of all. What if dark matter does not exist and our understanding of gravity itself is incomplete? A theory called modified Newtonian dynamics, or MOND, proposes that on the vast, gentle scales of galaxies, gravity behaves differently than Newton or Einstein predicted. It gets slightly stronger, eliminating the need for an invisible substance. For MOND supporters, a galaxy like NGC 1052DF2, where visible mass alone seems sufficient, is not an anomaly, it is a prediction. They argue it is the galaxies with apparent dark matter that are the odd ones out, requiring explanation. The discovery sent shockwaves through astronomy, not just for the galaxy itself, but for what it implied about our cosmic maps. If one galaxy can exist without dark matter, then dark matter is not an inviolable law. It is a physical substance that can be separated, removed, or perhaps never acquired. It turns an absolute into a variable, and that changes everything. The hunt is now on to find more of these dark matter-free ghosts, to see if they are cosmic mistakes or signposts to a deeper truth about the forces that sculpt our universe. The implications of a galaxy without dark matter were so profound that skepticism was not just expected, it was essential. The very first line of attack focused on a single, critical number, the distance to NGC 1052DF2. Distance is everything in astronomy. Get it wrong, and all other calculations about an object's mass, size, and brightness fall apart. The original team placed the galaxy about 65 million light-years away. If other astronomers could prove it was much closer, then its stars would be intrinsically fainter than assumed. This would mean the galaxy actually had far less visible mass, and the slow-moving globular clusters would suddenly require a huge amount of unseen, dark matter gravity after all. The controversy raged in scientific journals for months, a high-stakes debate over a few pixels of light. Rival teams reanalyzed the data, proposing the galaxy could be as close as 42 million light-years. At that distance, the dark matter mystery would simply vanish. Science, however, has a way of converging on the truth through relentless scrutiny. Follow-up studies, using more precise methods and powerful telescopes like Hubble, meticulously measured the galaxy's distance. They examined the subtle flickers of individual stars and the overall glow of the stellar population. The consensus that emerged strongly reaffirmed the original, more distant measurement. NGC 1052DF2 was indeed far away, and its stars were truly as bright and massive as first thought. The dark matter deficit was real. Then, as if to silence the last of the doubters, the same research team found another one. In the same patch of sky, near the same massive elliptical galaxy, they identified NGC 1052DF4. It was another ultra-diffuse ghost, and it too showed the same shocking signature, globular clusters drifting slowly in orbits that could be explained by stars alone. One galaxy could be a fluke, a cosmic oddity. Two, especially in the same neighborhood, pointed to a pattern, a new class of object. So how do you build a galaxy without the universe's most essential construction material? The leading theory points to a violent and complex birthing process within a dense galactic environment. Both of these anomalous galaxies reside near a giant elliptical galaxy called NGC 1052. Picture this region not as serene space, but as a chaotic construction site with immense gravitational tides. The theory suggests that long ago, dense clouds of gas were pulled into this tumultuous zone. As they swirled and clashed near the massive galaxy, the dark matter and the normal, star-forming gas within these clouds may have been violently separated. The dark matter, being immune to the friction and pressure that affects normal matter, could have been flung away on wide orbits while the gas was compressed, collapsed, and ignited into stars. The result was a born orphan, a galaxy of stars that formed already divorced from its dark matter halo. Alternatively, some models suggest these galaxies did have dark matter initially, but the relentless gravitational pull of their massive neighbor slowly and completely stripped it away over billions of years, a process so efficient it left the stellar population surprisingly intact. The mystery now shifts from a question of existence to a question of abundance. Are NGC 1052DF2 and its sibling rare freaks the cosmic equivalent of a genetic mutation? Or are they simply the first of many, hinting that our standard model of galaxy formation is far messier and more diverse than we imagined? Finding more of these ghosts is the next great challenge. Each new discovery will help astronomers map out the conditions needed to create such an object. They become critical test cases, natural experiments that show us what happens to a galaxy when you remove its invisible skeleton. Do they fall apart? Do they evolve differently? Their very existence, whether common or rare, forces us to ask the most fundamental question of all. Is dark matter a physical substance that can be manipulated and removed, or is it an inseparable part of the cosmic fabric? These faint, see-through galaxies are now at the forefront of that battle, silent witnesses in a debate that will define our understanding of the universe's hidden architecture. The faint ghosts of galaxies without dark matter challenge our maps of the cosmos, but sometimes the universe does not hide its mysteries in subtle omissions. It grabs the entire galactic neighborhood and pulls. Our Milky Way galaxy is not drifting aimlessly through the void. It is racing along with our entire local group of galaxies and countless others toward a specific, terrifying point in space. Astronomers call it the Great Attractor. Picture the grandest river you can imagine, a flow of galaxies millions of light years across, all streaming toward a single, invisible waterfall. This gravitational anomaly lies in the direction of the constellations Centaurus and Norma, and its pull is equivalent to the combined gravity of tens of thousands of galaxies like our own. The discovery unfolded slowly, a puzzle pieced together in the 1970s and 80s. Scientists were meticulously mapping the faint afterglow of the Big Bang, the cosmic microwave background. This radiation should be uniform in all directions, a perfect echo of the infant universe, but they found a subtle yet unmistakable dipole anisotropy. One half of the sky was very slightly warmer, the other slightly cooler. The simplest explanation was motion. Our galaxy and everything attached to it was moving at over 600 kilometers per second relative to this primordial backdrop. We were not just orbiting within our local group, we were on a colossal journey. Where were we going? The answer came from mapping the peculiar velocities of thousands of galaxies around us, tracing the flows of this cosmic river. All paths led toward a specific region of space, a gravitational focal point of unimaginable density. The mystery deepened because we could not see it. The Great Attractor lies directly behind the plane of our own Milky Way, in a zone astronomers call the zone of avoidance. This is the dusty, star-choked central disk of our galaxy, which acts like a thick cosmic fog, blotting out the visible light from anything behind it. It was like hearing the roar of a colossal waterfall from just beyond an impenetrable jungle. We could feel its immense gravitational pull, bending the paths of entire galaxies, but our optical telescopes were blind. The initial calculations were staggering. The visible mass observed in that general direction, the few galaxies we could peek around the dust to see, was nowhere near enough to account for the gravitational force required. Something with the mass of a supercluster, tens of thousands of times the mass of the Milky Way, had to be there, hidden in the shadows of our own galactic backyard. What could possibly have that much mass, and why was it so effectively concealed? The hunt was on to see the unseeable, to map the architecture of this monstrous gravitational anchor pulling us all toward an unknown fate. Our blindness to the great attractor was not a permanent sentence. To see through the cosmic fog of our own galaxy, astronomers had to change their eyes. They turned from visible light to wavelengths that slice effortlessly through interstellar dust, radio waves, and infrared. Pioneering surveys in the 1990s, like the H.I. Park's All-Sky Survey, used radio telescopes to map the distribution of neutral hydrogen gas in thousands of galaxies hidden behind the Milky Way's plane. This was like switching from a flashlight to an X-ray machine. The hidden landscape began to emerge, and it revealed not a single monstrous object, but something far grander. The great attractor was not a thing. It was a place, the gravitational heart of our home. We live within a supercluster of galaxies so vast it needed a new name, Laniakea, a Hawaiian word meaning immense heaven. This is our true cosmic address. Laniakea spans over 500 million light-years and contains more than 100,000 galaxies, all bound together in a gentle, mutual gravitational embrace. Its structure resembles a colossal cosmic watershed. Picture a mountainous landscape after a heavy rain. Individual streams flow into creeks, creeks into rivers, and all rivers eventually pour into a single vast basin. In Laniakea, every galaxy, including our Milky Way, is like a droplet of water. We are part of a local stream called the local group, which flows into the larger river of the Virgo cluster, and all these galactic rivers are sliding down the gravitational slopes toward the same deep basin, the Norma cluster, which sits at the supercluster's dense core. This is the great attractor. Its immense pull is not from one unseen monster, but from the combined, staggering mass of all those 100,000 galaxies, and more importantly, the titanic dark matter halos that envelop them. The mystery was solved by revealing a structure of almost incomprehensible scale. Yet, in solving one puzzle, we uncovered a larger one. Laniakea itself is not stationary. Our entire immense heaven is in motion, pulled by an even greater source of gravity. Astronomers have mapped this larger flow, and it leads toward a concentration of mass known as the Shapley supercluster, the most massive collection of galaxies in our nearby universe. We are caught in a relentless cosmic tug-of-war. The great attractor pulls us inward toward the heart of Laniakea, while the distant Shapley attractor pulls Laniakea itself. We are like a leaf in a vast, multi-layered drainage system moving toward a local basin, while the entire basin is itself drifting toward a continental sea. This transforms the anomaly from a search for a hidden object into a profound lesson in cosmic perspective. The great attractor was never a destination but a signpost. It revealed our place in a hierarchical universe where galaxies gather into clusters, clusters into superclusters, and superclusters into filaments that make up the great cosmic web. The force we felt was simply gravity doing what it does on the grandest scales, weaving the visible universe into a structured, flowing tapestry. Our journey toward it is not a headlong rush into a black hole, but a stately, billion-year drift within our home supercluster. And that home itself is on the move, forever answering the call of larger structures in the dark. Gravity's grand tug-of-war between superclusters operates on scales of hundreds of millions of light-years. But sometimes the most stubborn mysteries are not found in the distant cosmos, but in the quiet, precise data coming from our own robotic envoys as they slip into the dark. For decades, a tiny, persistent puzzle plagued NASA engineers. The Pioneer 10 and Pioneer 11 spacecraft, having completed their historic flybys of Jupiter and Saturn, were now on their way out of the solar system. They were slowing down just a bit more than predicted by gravity alone. This minuscule deceleration, about 8.74 times 10 to the negative 10 meters per second squared, became known as the Pioneer anomaly. To grasp how small this force was, imagine the gentle pressure of a single sheet of paper resting on your hand. That is roughly the scale of the unaccounted for push acting against a 1,000-pound spacecraft billions of miles away. Yet, over years and decades, this whisper of a force added up, creating a navigational discrepancy that grew to thousands of kilometers. These pioneers of deep space, launched in the 1970s, were tracked with exquisite precision. Engineers used the radio Doppler shift, the same principle that makes a siren's pitch change as it passes you, to measure their velocity. By monitoring the precise frequency of the radio signals beamed back to Earth, they could calculate the spacecraft's speed down to a fraction of a millimeter per second. The data was unambiguous. Something was ever so slightly holding the probes back. The discrepancy was tiny but maddeningly consistent, suggesting either an unknown force or a fundamental flaw in our understanding of physics at the very large, very quiet scales of the outer solar system. The implications were profound. Could this be the first hint of a new physical effect? Theories flourished, ranging from the exotic to the mundane. Some physicists proposed it was evidence of dark matter drag, a gentle friction from the invisible halo of our galaxy. Others wondered if it pointed toward a modification of gravity itself, like the modified Newtonian dynamics theory that sought to explain galactic rotation without dark matter. Perhaps Einstein's theory of general relativity needed a slight tweak at the vast distances where the sun's gravity grows incredibly weak. Yet, the most likely explanations were far more ordinary, and they centered on the spacecraft themselves. Pioneer 10 and 11 were not sleek, modern probes. They were nuclear-powered, boxy machines with large dish antennas pointed steadily at Earth. Their electricity came from radioisotope thermoelectric generators, which produced heat as a byproduct. That heat had to go somewhere. The leading mundane theory suggested thermal radiation pressure. Picture the spacecraft as a simple kitchen light bulb. It emits light we can see, but it also emits infrared radiation, which is just heat. Every photon of that infrared radiation, as it streams away from the spacecraft, carries a tiny amount of momentum. If the heat radiates unevenly, more from one side of the craft than the other, it can create a net push. In the case of the pioneers, if more heat was radiating from the back of their dish antennas, pushing toward Earth, it would act as a constant, tiny brake, perfectly mimicking an anomalous deceleration. Other ideas included a minuscule fuel leak from their attitude control thrusters, or even the gentle pressure of the solar wind. For years, the debate raged between the revolutionary and the routine. Solving it would require not a new telescope, but a forensic excavation of old engineering documents and a painstaking reconstruction of the probe's thermal blueprints, a digital archaeology project to understand the ghosts in the machine we had built ourselves. The ghost in the machine was finally found, not in the equations of gravity, but in the blueprints for heat. For years, the Pioneer anomaly was a tantalizing loose thread in the fabric of physics, a whisper that perhaps our understanding of the cosmos was incomplete. The solution, however, demanded a shift in perspective, from the cosmic to the microscopic, from the force of gravity to the gentle push of light. It required scientists to become forensic engineers, digging through decades-old design documents to rebuild a digital twin of each Pioneer spacecraft, bolt by bolt, wire by wire. Their focus was the spacecraft's power source, the radioisotope thermoelectric generators. These nuclear batteries produced electricity from the steady decay of plutonium-238, but that process also generated a constant, substantial amount of waste heat, over 2,000 watts of it. That heat had to escape into space, and it did so as infrared radiation, a stream of invisible photons. Each photon, as it shot away from the spacecraft, carried a tiny amount of momentum. According to Newton's third law, for every action there is an equal and opposite reaction. So, as the photon flew away in one direction, it gave the spacecraft a minuscule nudge in the opposite direction. Normally, if a spacecraft were a perfect, symmetrical sphere radiating heat evenly in all directions, these nudges would cancel out, but the Pioneers were anything but symmetrical. They were complex machines with large parabolic dish antennas permanently pointed at Earth, and their electronics boxes were mounted on the main body. The critical insight was that the back of that large dish antenna acted like a radiant heater. More waste heat was being reflected and radiated off the back of the dish, which faced away from the sun and toward deep space than from the front. This created an imbalance, an anisotropic thermal radiation field. The spacecraft was in effect a very faint photon rocket with its engine pointed roughly toward Earth. The constant stream of photons pushing off the back of the dish created a tiny but relentless force that acted as a brake, slowing the pioneers on their journey outward. When teams finally completed their painstaking thermal models in the 2000s and early 2010s, factoring in the exact placement of every component and how heat would conduct through the structure and radiate away, the numbers aligned. The calculated push from this thermal recoil matched the observed anomalous deceleration almost exactly. The case was closed. The Pioneer anomaly was not a flaw in Einstein's universe, but a testament to the incredible precision of our measurements. We had built machines so well and tracked them so accurately that we could detect the force of their own body heat pushing back against them across billions of miles. Yet, even in closure, a sliver of mystery lingers. Some analyses suggest the thermal model accounts for most of the anomaly, but perhaps not all of it. A tiny residual effect, a fraction of that original signal, might still be unaccounted for. This lingering doubt is the anomaly's final lesson. It reminds us that in the extreme quiet of interstellar space, where the sun's gravity is a faint whisper and solar wind pressure has faded, the smallest details matter. A flake of paint, a microscopic fuel leak, or the exact angle of a reflective surface can become the dominant force. The pioneers taught us that to navigate the true depths of space, we must become masters not just of rockets and orbits, but of thermodynamics and engineering down to the most minute detail. Their solved mystery stands as a monument to human ingenuity, a story where we first suspected a revolution in physics, but ultimately discovered we had simply underestimated the subtle craftsmanship of our own machines. The pioneers taught us to listen to the whispers of our own machines, but other spacecraft seemed to be getting secret messages from Earth itself. This is the flyby anomaly, a fleeting and unpredictable ghost in the gravity assist. For decades, mission planners have used our planet as a cosmic catapult. By carefully steering a spacecraft close to Earth, they can steal a tiny fraction of our orbital momentum, flinging the probe toward its distant target with increased speed. The physics of this gravity slingshot is considered textbook, calculated down to the millimeter. Yet, when engineers tracked spacecraft like Galileo, Near, and Rosetta during these critical flybys, the numbers did not quite add up. After whipping around Earth, their velocities were off by a tiny but undeniable amount, a discrepancy of just a few millimeters per second. To grasp that scale, think of a car traveling at highway speed gaining an extra thickness of a coin per hour. It is negligible for a road trip, but over an interplanetary voyage spanning years and billions of miles, such an error can mean missing a planet entirely. The anomaly was not even consistent. Sometimes the spacecraft gained a tiny, unexpected speed boost. Other times it emerged slightly slower than predicted. The Galileo probe provided the first strong hints during its Earth flybys in 1990 and 1992. Post-flyby tracking showed a speed difference that stubbornly refused to be explained by known factors like atmospheric drag or solar radiation pressure. But the clearest, most puzzling signature came from the Rosetta spacecraft in 2005. On its long journey to rendezvous with a comet, Rosetta performed an Earth gravity assist, swinging by at an altitude of just over 1,900 kilometers. The tracking was exquisite, using a global network of radio telescopes. When the data was in, the anomaly was unmistakable. Rosetta's speed had increased by about 1.8 millimeters per second, more than all the complex models had forecast. What could possibly account for such a precise yet baffling mismatch? The immediate suspects were errors in our map of Earth itself. Perhaps our models of Earth's gravity field, which is not a perfect sphere but a lumpy potato shape, were still incomplete. Tiny variations in mass distribution deep within the planet could subtly alter a spacecraft's trajectory. Another exotic possibility involved Earth's rotation. Einstein's theory of general relativity predicts that a massive rotating body like our planet drags spacetime around with it, an effect called frame dragging. Could this relativistic swirl be imparting an extra nudge that our standard equations missed? Some researchers even look to planetary secrets, wondering if a faint, extended atmosphere of dark matter or some other unseen halo around Earth was providing an extra gravitational tug. Yet, as with the Pioneer puzzle, the most compelling answers may lie in the details we overlook. Later analyses suggested that more careful modeling of thermal effects could explain a large part of the Rosetta anomaly. As the spacecraft passed from Earth's shadow into full sunlight, the uneven heating and cooling of its surfaces could cause minute expansions and contractions, changing its reflective properties and thus how it interacted with solar radiation pressure. Other proposals pointed to subtle tidal forces from Earth's oceans or even the gentle pressure of Earth's own thermal radiation. Each flyby is a unique ballet of orientation, speed, and geometry, meaning these tiny forces could add up differently every time, explaining why the anomaly seems to come and go. The flyby anomaly, therefore, stands as a monument not to broken physics, but to the astonishing precision of modern orbital science. It reveals that in the high-stakes game of interplanetary navigation, we are now playing in a realm where the spin of our planet, the heat of our sun, and the very warmth radiating from our own world must all be accounted for in the ledger. That phantom millimeter-per-second push on Rosetta was no isolated event. The flyby anomaly persists as one of the most stubborn puzzles in orbital mechanics precisely because it refuses to be pinned down. Its sporadic nature, appearing for some spacecraft and not others or with different magnitudes, points not to a single dramatic new force, but to a subtle cumulative error in our accounting. The hunt for its source has become a meticulous process of elimination, forcing scientists to question every line in their complex gravitational ledger. The prime suspect has long been our own planet's hidden contours. Earth is not a perfect, smooth sphere. It is a lumpy, dynamic geoid with mountains, ocean trenches, and uneven densities in its mantle and core. Our best gravitational maps, built from decades of satellite data, are incredibly detailed, but they are not perfect. Could a tiny, unmapped concentration of mass, a gravitational pothole, be giving spacecraft an uncalculated nudge as they whip past? The challenge is that the anomaly's signature is so minute that it sits right at the edge of our mapping precision. Atmospheric drag is another obvious culprit. Even at altitudes of 1,000 kilometers where these flybys occur, there are trace remnants of Earth's exosphere. The drag from these wispy atoms is minuscule, but perhaps during a particularly active solar cycle, the atmosphere expands just enough to create a detectable, if tiny, break. Yet, models of atmospheric density struggle to fully explain the observed speed changes, especially the ones that seem to add energy. Then there are the more exotic entries on the suspect list. Could relativistic effects like the frame dragging caused by Earth's rotation be imparting a slight torque we have not fully modeled? Or perhaps the gentle, cumulative pull of ocean tides flexing the planet's crust creates a fluctuating gravity field that our static models miss? Some theorists have ventured even further, proposing that Earth might be ensconced in a faint, localized halo of dark matter. If our planet has gravitationally captured a cloud of these invisible particles, a spacecraft plunging through it could experience an extra fleeting tug. This idea, while speculative, underscores how deeply the anomaly challenges our assumptions. To settle the debate, scientists needed a perfect test case, a modern spacecraft performing a clean, passive flyby with its thrusters completely silent. All eyes turned to the Juno mission. In October 2013, Juno used an Earth gravity assist to slingshot toward Jupiter. This was a golden opportunity. Teams around the world coordinated to track Juno with unprecedented precision before, during, and after its closest approach. Unfortunately, the experiment was compromised. To maintain its crucial orientation, Juno's reaction control thrusters fired periodically throughout the flyby. These tiny pulses of thrust, essential for the spacecraft's survival, injected noise into the Doppler tracking data, muddying the signal of any potential anomaly. The results, while valuable, were ultimately inconclusive. They could neither confirm nor rule out the anomaly's presence. This outcome, in a way, is the perfect epitaph for the flyby anomaly so far. It highlights the exquisite difficulty of the search. We are chasing a whisper in a hurricane of complex, interacting forces: thermal, gravitational, and human-made. Each future gravity assist, whether by a mission to the outer planets or an asteroid sample return, will now be an opportunity. Mission planners and orbital dynamicists will scrutinize the tracking data, refining their models of Earth's geoid, the tenuous outer atmosphere, and relativistic effects. The anomaly ensures we can never be complacent. It is a permanent reminder that in the silent calculus of celestial navigation, even a planet we call home can still hold a few secrets, subtle enough to be measured only in the thickness of a coin over an hour, but profound enough to remind us that precision is a journey, not a destination. The silent precision of Earth's flyby calculations exists in a realm of millimeters and milliseconds, but on Saturn, the atmosphere performs geometry on a scale that dwarfs our entire planet. At the gas giant's north pole, a perfect and permanent hexagon is etched into the clouds, a shape so precise it seems manufactured. This six-sided jet stream was first glimpsed by the Voyager probes in the 1980s, a blurry, puzzling feature that many assumed was a temporary fluke. Decades later, NASA Cassini spacecraft arrived at Saturn and turned its cameras toward the North Pole, revealing the hexagon in breathtaking, terrifying detail. It is a colossal structure about 30,000 kilometers across, meaning two Earths could fit side by side within its boundaries. Its walls are sheer cliffs of cloud, with winds screaming along its edges at over 300 miles per hour. And at its very center sits a churning, hurricane-like vortex, a storm with an eye 50 times larger than any hurricane eye on Earth. The most staggering fact is its endurance. This is not a fleeting weather pattern. It has been there, spinning in perfect geometric lockstep for at least 4 decades of human observation, and likely for centuries or more. The fundamental mystery is stark and simple. Why a hexagon? On Earth, atmospheric patterns driven by rotation, like hurricanes or the jet stream, are circular or meandering. Chaos and curves are the norms of planetary weather. A stable, persistent polygon defies our basic intuition. To solve this, scientists had to move from the planetary scale to the laboratory bench, using rotating fluids to simulate the dynamics of Saturn's atmosphere. In experiments, when a circular tank of fluid is spun at different speeds between its center and its outer edge, something remarkable happens. Under the right conditions, the flowing liquid does not form a smooth, circular pattern. Instead, it snaps into a stable polygonal shape with a number of sides depending on the difference in rotation speeds. A hexagon is a common, naturally emerging pattern in these controlled experiments. The physics hinges on shear, the difference in velocity between adjacent streams of fluid. On a rapidly rotating planet like Saturn, where the poles and the lower latitudes spin at nearly the same rate but the atmosphere moves at different speeds, these shearing layers can become unstable. That instability can organize itself not into random turbulence, but into a standing wave, a stable pattern of peaks and troughs. On Saturn, the hexagon's walls are essentially these towering planetary scale waves, frozen in place by the planet's furious rotation. So the mystery is partially solved. We know the laboratory conditions that can create a hexagon, but replicating the sheer scale and immortal stability of Saturn's version within a real, chaotic, planet-sized atmosphere remains a monumental challenge. Our models can create a temporary hexagon, but they struggle to maintain it for the equivalent of Saturn's long seasons. This suggests there are deeper stabilizing factors at play, perhaps related to the planet's internal heat flow or the unique composition of its polar atmosphere. Saturn's hexagon, therefore, is more than a beautiful curiosity. It is a natural laboratory of fluid dynamics writ large across the sky of a world. It proves that the universe has a hidden fondness for order, that even in the raging chaos of a gas giant's weather, mathematical precision can emerge and endure, a six-sided sentinel standing watch over a pole of perpetual storm. Saturn's hexagon is not merely a skin-deep tattoo on the clouds. When the Cassini spacecraft peered beneath the visible cloud tops using infrared and other instruments, it made a startling discovery. This geometric wonder is not a superficial pattern. It is a deep-seated atmospheric structure, a towering wall of wind and weather that extends hundreds of kilometers down into the planet's murky interior, possibly reaching all the way to the base of Saturn's weather layer. This depth is a crucial clue. It tells us the hexagon is not a fleeting surface feature, but an integral part of the planet's atmospheric machinery, rooted in the fundamental dynamics of the gas giant itself. The engine driving this phenomenon is Saturn's furious rotation. A day on Saturn is only about 10.5 hours long, despite the planet being nearly 10 times wider than Earth. This rapid spin stretches and organizes the atmosphere into distinct bands of eastward and westward flowing jet streams. The hexagon sits precisely at the boundary of one of these most intense jet streams, a place where wind shear, the difference in velocity between adjacent atmospheric bands, is extreme. Think of it as the planetary equivalent of two mighty rivers flowing side by side at vastly different speeds. The turbulence where they meet does not create random chaos, but under the right conditions, it can snap into a stable, resonant pattern, a standing wave frozen in place by the planet's spin. At the very heart of this six-sided storm sits another marvel, the central hurricane. This vortex is not passive. Its eye-wall clouds tower high above the surrounding hexagon, a massive, churning engine that likely plays a key role in stabilizing the entire system. The hurricane and the hexagon are locked in a complex gravitational and aerodynamic dance, each influencing the other's structure and persistence. So is the hexagon simply a standing wave? Laboratory experiments with rotating fluids strongly suggest it is. When scientists spin a tank of liquid, varying the rotation speed between the center and the outer edge, they can reliably produce polygonal shapes, with hexagons being a common and stable outcome. This confirms that the basic physics is understood, yet replicating the sheer scale, the breathtaking precision, and the decades-long stability of Saturn's version in a real-world, planet-sized atmosphere remains an immense challenge. Our models can create a temporary hexagon, but they struggle to maintain its razor-sharp geometry against the inevitable buffeting of planetary-scale turbulence. The exact recipe of wind speeds, atmospheric densities, internal heat flow, and planetary rotation that cooks up this perfect, persistent geometric storm is still not fully written. Saturn's hexagon, therefore, stands as a beautiful enigma. It is a natural theorem written in wind and cloud, proving that order can spontaneously emerge from chaos on a scale that humbles our imagination. It is a reminder that some of the universe's most precise artwork is not found in the quiet of deep space, but in the raging hearts of giants. Geometric perfection carved by a dying star defies every expectation of a nebula's final breath. In the constellation Monoceros, the celestial unicorn, the Hubble Space Telescope captured an object so bizarrely symmetrical it seems drawn by a cosmic architect, the Red Rectangle Nebula. Its name, while accurate, fails to capture its true strangeness. At its heart glows a vivid red rectangle, but extending from it are two brilliant, ladder-like rungs forming a near-perfect X shape, as if someone had sketched a three-dimensional hourglass with a straight edge. This is not the gentle, wispy glow of most nebulae. This is geometry written in light and gas, a structure so precise it feels intentional. The object is a protoplanetary nebula, a fleeting phase in a star's death. The central star, known as HD 44179, has exhausted its nuclear fuel and is shedding its outer layers into space. Normally, this process creates either a roughly spherical shell or a bipolar shape, two lobes billowing from the star's poles like an hourglass. The red rectangle is neither. Its secret and the source of its impossible shape lies in a dance of two stars, not one. HD 44179 is part of a tight binary system. Its companion is a small, dense white dwarf, and together they orbit each other in a complex gravitational waltz. As the dying star puffs away its atmosphere, this expelled material does not flow out evenly. Instead, the companion star's gravity and the system's rotation funnel the gas and dust into two narrow cones, shooting out from the poles of the dying star like twin searchlights. But there is a second, crucial component, a dense, donut-shaped ring of dust and gas, a torus that wraps tightly around the star system's waist, right at its equator. This torus acts like a cosmic corset, squeezing the polar outflows, constricting them into exceptionally narrow and well-defined jets. Now, picture this intricate structure from the side, with our line of sight looking almost directly at the edge of this dense dust belt. What we see is the conical outflows above and below the torus, their edges appearing as the two bright rungs of the X. The central red rectangle is the glow of starlight reflected and reddened by the thick dust in the torus itself, its rectangular illusion created by the precise shadows and openings within this pinched system. So the mystery resolves into a breathtaking celestial sculpture where binary dynamics and a dust belt collaborate to carve a temporary masterpiece, yet a profound question lingers. Why is this geometry so sharp, so nearly perfect, when most other bipolar nebulae show soft, billowing curves? The answer may lie in the precise alignment and stability of this particular system, a fleeting moment of cosmic balance where outflow, gravity, and obscuration align to create an optical illusion of mathematical purity. The red rectangle is not a permanent monument. In a few thousand years, the central stellar core will heat up, illuminating the expelled gas to become a full-fledged planetary nebula, likely blurring these crisp lines forever. We are witnessing a snapshot of sublime order in the chaotic process of stellar death, a reminder that even in its final act, a star can leave behind a signature of unexpected and precise beauty. That precise geometry is a frozen moment in a gravitational ballet. The red rectangle's sharp X shape and ladder-like rungs are not a static sculpture, but a dynamic record of a stellar partnership in its final act. The secret lies in the intricate dance between its two central stars. One is a dying red giant, bloated and shedding its outer layers. The other is a smaller, denser companion, likely a white dwarf locked in a tight orbit. As the red giant swells, its outermost atmosphere gets gravitationally stolen by its partner. This stolen material doesn't just fall onto the companion star. Instead, it forms a swirling, superheated disk of gas around it, an accretion disk. This disk acts like a cosmic nozzle, channeling and focusing some of the outflow into two narrow, opposing jets that shoot out from the system's poles. Meanwhile, a thick belt of dust and gas encircles the entire binary pair at its equator, further squeezing and collimating these polar outflows into the stark, conical shapes we see. The result is a pair of searchlight beams of gas and dust projected into space with extraordinary precision. But what about those distinctive rungs, the glowing concentric rings that make the nebula look like a celestial ladder? These are thought to be the echoes of periodic eruptions. Every few hundred years, as the accretion disk around the companion star becomes unstable or the red giant experiences a particularly strong pulse, a new shell of material is violently ejected. This shell expands into the older outflow, creating a shock wave that lights up like a ring of neon. Over millennia, these periodic puffs have stacked up, creating the nested, ladder-like structure captured in Hubble's iconic image. We are seeing a stellar death recorded in pulses, a timeline written in concentric rings of light. This masterpiece, however, is temporary. The central red giant is steadily exhausting its fuel. In the relatively near future, perhaps within a few thousand years, its exposed core will heat up dramatically, flooding the surrounding nebula with intense ultraviolet radiation. This radiation will rip electrons from the atoms in the gas, causing it to fluoresce in brilliant blues and greens. The red rectangle will transform, its crisp geometric lines likely softening and blurring as the gas becomes fully ionized. It will evolve into a more traditional-looking planetary nebula, a glowing shell surrounding a tiny, hot white dwarf. For now, though, it remains a unique and pristine laboratory. It allows astronomers to study the precise mechanisms by which binary stars choreograph death into art, showing us that even in its final throes, a star system can produce a legacy of breathtaking mathematical beauty. The geometric death of a binary star is a slow, precise sculpture, but a single, massive star can threaten to erase its entire neighborhood in a flash. In the winter of 2019, one of the night sky's most familiar beacons began to fade. Betelgeuse, the brilliant red supergiant marking the shoulder of the constellation Orion, was vanishing before our eyes. By February 2020, its light had dimmed by an astonishing 65%, a change so dramatic that backyard stargazers could see it with their own eyes. For centuries, this star had been a textbook example of a variable star, known to pulse in brightness over a rough 400-day cycle, but this was different. This was not a gentle rhythm. This was a plunge into darkness deeper than any recorded in over a century of precise observation. The question electrified the world: was this the final act? Was Betelgeuse, a star nearing the end of its life and only about 700 light-years away, about to explode as a supernova? The possibility was both terrifying and thrilling. A supernova from such a relatively close star would be a celestial event for the ages, potentially visible in broad daylight and outshining the full moon at night. Telescopes across the globe and in space immediately swiveled toward Orion. Astronomers used every tool at their disposal, from visible light to infrared and ultraviolet, desperate to read the star's vital signs. Early theories were suitably dramatic. Perhaps a gigantic star spot, a dark region cooler than the surrounding surface, had bloomed across a massive portion of the star's face. Or maybe the star was experiencing deep convulsions, ejecting vast amounts of material in a pre-supernova fever. For months, Betelgeuse hung there, dim and enigmatic, a cosmic suspense story written in the slow fading of a single point of light. The world watched, wondering if the next clear night might bring a spectacle unseen in our galaxy since the time of Kepler. The suspense finally broke not with a bang, but with a detailed analysis of starlight. As Betelgeuse slowly returned to its normal brightness over the spring of 2020, astronomers had their answer. The culprit was not a star spot or a final death rattle, but something more mundane and yet profoundly illuminating: dust. Observations from the Very Large Telescope in Chile captured high-resolution images of the star's surface, and they revealed something startling. The southern hemisphere of Betelgeuse had dramatically darkened. This was not a uniform dimming, but a localized event. The leading explanation paints a vivid picture of a star's inner turmoil. Betelgeuse is a seething cauldron of convection, with massive bubbles of hot plasma constantly rising from its interior to the surface. One of these convective cells, larger than our entire solar system, is thought to have surged upward with extraordinary force. It carried an immense amount of hot stellar material to the surface, where the environment is far less dense. There, in the cold of space, this ejected gas rapidly expanded and cooled. As it cooled, some of the heavier elements within it, like silicon and aluminum, condensed directly from gas into solid particles, forming a vast cloud of silicate and aluminum oxide dust. This cloud, billowing from the star's southern region, drifted between Betelgeuse and our line of sight, acting like a cosmic veil and dimming the star's light. In essence, Betelgeuse had a stellar sneeze, ejecting a cloud of stellar soot that temporarily obscured its face. This solved the immediate mystery, but the implications were far greater. The event provided a front-row seat to the very process by which red supergiants lose mass in their final years. Each of these convulsive ejections strips away part of the star's outer layers, gradually preparing it for the ultimate explosion. We learned that Betelgeuse is not quietly fading, it is violently shedding its skin in episodic fits, and we happened to witness one of its most dramatic episodes. So while the Great Dimming was not a prelude to a supernova, it was a critical rehearsal. It taught us that even the most familiar stars in our sky lead dramatic, hidden lives, their stability and illusion masking a constant struggle. Betelgeuse's eventual fate is sealed, a supernova that will light up our sky within the next 100,000 years, a cosmic time bomb whose fuse we are now learning to watch burn. Betelgeuse's violent sneeze was a local event, a single star clearing its throat. But what if an entire region of the cosmos, a volume of space so large it defies comprehension, was simply and profoundly empty? In the grand architecture of the universe, galaxies are not scattered randomly like salt. They are woven into a vast cosmic web, a lacework of brilliant filaments and dense clusters surrounding enormous, dark bubbles of nothingness. These are the cosmic voids, and among them one stands as a king of emptiness, the Bootes void. Discovered in the early 1980s, this spherical region of space is about 330 million light-years across. To grasp that scale, if our Milky Way sat at the very center of this void, humanity would not have discovered another galaxy until the 1960s. For nearly all of human history, our telescopes would have peered into a perfect, starless black in every direction. This is not a metaphor. The Bootes void is a real and staggering near emptiness. When first mapped, astronomers found only a handful of galaxies in a volume of space where the standard model of the cosmos predicted there should be thousands. It was not just underpopulated, it was a galactic desert on a scale that seemed to break the rules. How does such a thing form? The cosmic web is thought to be the result of tiny quantum fluctuations in the earliest moments of the Big Bang, magnified by gravity over billions of years. Dense regions attracted more matter, becoming filaments and clusters, while the underdense regions were left behind, evacuated by gravity's pull. But the Bootes void is so exceptionally large and empty that it pushes this idea to the limit. Could random chance alone produce a void this vast and barren, or does its existence force us to consider more exotic possibilities? Some theorists have suggested it might be the imprint of a pre-Big Bang phenomenon, or the result of a collision between universe-sized bubbles in the multiverse. Others propose it is simply the largest statistical fluctuation in our observable universe, a 1 in a trillion cosmic lottery ticket we happen to draw. The mystery has deepened with more careful observation. The void is not completely empty. Later surveys have found perhaps 60 galaxies drifting in that immense darkness, but that is still a pitiful number, like finding 3 grains of sand in an aircraft hangar. These lonely galaxies are themselves peculiar, often isolated and oddly quiet, as if the void itself has stunted their growth. Their very existence raises new questions. Did these galaxies form here, struggling to gather material in this desert? Or are they the stranded survivors of a larger population that was somehow cleared out? The Bootes void is more than a curiosity. It is a stress test for our models of cosmic evolution. If our understanding of structure formation is correct, voids this large should be exceedingly rare, perhaps too rare to exist in the volume of space we can observe. Its presence challenges cosmologists to refine their simulations, to see if the subtle interplay of dark matter, dark energy, and ordinary matter can naturally sculpt such a perfect sphere of nothing. It stands as a monument to the universe's capacity for both extravagant structure and profound absence, a silent bubble in the cosmic foam that makes us wonder what other immense patterns we have yet to see. Those few galaxies adrift in the Boots void are not merely lonely, they are cosmic fossils. Unlike the bustling, metal-rich spirals and ellipticals found in clusters and filaments, the void's isolated inhabitants are often gas-rich, irregular, and possess low metallicity. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium. Since these heavier elements are forged in stellar furnaces and spread by supernova, a low metallicity indicates a galaxy that has experienced very little star formation over its lifetime, or one that formed from pristine, early universe gas. These galaxies are like isolated tribes that never traded with the outside world, preserving ancient conditions. They are relics offering a direct window into what the first galaxies might have looked like before the cosmic web became enriched with the recycled material of countless stellar generations. Their very existence in the void raises a chicken and egg question. Did the void's emptiness stunt their growth, preventing them from merging with others and forming grand spirals? Or were they simply born in this desert from the meager scraps of matter left behind when everything else was gravitationally swept away? To explain the void's existence, cosmologists look to the violent sculpting of the early universe. The leading theory suggests it is not a single primordial bubble, but a colossal structure formed by the merger of multiple smaller voids. Over billions of years as the cosmic web evolved, the walls between adjacent underdense regions could have thinned and broken, allowing the empty spaces to coalesce into one staggering sphere of nothing. It is a sobering thought that emptiness itself can grow and merge, creating ever larger deserts. More speculative ideas venture into the realm of cosmic archaeology, suggesting the void could be the imprint of a phase transition in the universe's first moments, a defect in the fabric of spacetime frozen into the distribution of matter. Some have even proposed, though it remains a fringe hypothesis, that it could be a scar from a gravitational interaction with a parallel universe in the multiverse, a notion that stretches the limits of testable science but captures the profound mystery such an object represents. Practically, the Boots void poses a direct challenge to the lambda cold dark matter model, our standard blueprint of the cosmos. While the model successfully predicts the web-like structure of the universe, it struggles to produce voids quite this large and quite this empty in the volume of space we can observe. Finding it is like rolling a die 100 times and getting a 1 every single time. It is statistically possible, but it makes you question the fairness of the die. This forces cosmologists to refine their simulations, tweaking the properties of dark energy or the initial conditions of the Big Bang to see if such a profound emptiness can naturally emerge. In the end, studying the Boots void is not about the emptiness itself, but about understanding the rules that govern everything else. It is like studying a desert to comprehend a rainforest. By probing the limits of where galaxies cannot form, we learn the essential conditions required for them to thrive. This colossal sphere of near-nothingness, therefore, is not an error in the cosmos. It is a critical experiment written across space, testing the very foundations of our cosmic story. The cosmic desert of the Boots void shows us emptiness on a scale that defies belief, but sometimes the universe sends a single, silent traveler right through our own backyard. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was unlike anything seen before, a hyperbolic arc that screamed it was not from here. This was Oumuamua, the first confirmed interstellar visitor to our solar system, a messenger from the vast spaces between stars. The name from Hawaiian appropriately means scout. Its initial detection was historic, but its true strangeness unfolded in the weeks that followed. First was its shape. By analyzing how its brightness changed dramatically as it tumbled, astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide, resembling a cosmic cigar or a flattened pancake. No asteroid or comet in our solar system looks like that. It was also a dark, reddish color, suggesting an ancient surface baked by cosmic rays over millions or billions of years. But the most profound mystery came as it was leaving. After whipping around the sun and heading back out to interstellar space, something unexpected happened. Precise tracking by the Hubble Space Telescope and ground-based observatories revealed a tiny but undeniable anomaly in its motion. Its path could not be explained by gravity alone. Oumuamua was experiencing a slight, additional acceleration, a gentle push away from the sun. This is called a non-gravitational acceleration. For comets, this is common. As they warm up near the sun, frozen ices on their surface turn to gas, jetting out like invisible engines and giving them a push. But Oumuamua showed no signs of this outgassing. No surrounding cloud of gas or dust, no cometary tail, nothing. It was accelerating in perfect, silent defiance of the known rules. This tiny push ignited a scientific firestorm. If it was not outgassing, what was providing the thrust? One exotic theory proposed it was a hydrogen iceberg. In the cold depths of interstellar space, a chunk of solid molecular hydrogen could form. As it neared the sun, the hydrogen would sublimate, providing a gentle push without producing a visible coma, since hydrogen is invisible to our telescopes. Yet, many physicists doubted such an object could survive the journey across the galaxy without evaporating. Then came the most provocative idea put forward by Harvard astronomer Avi Loeb. He suggested that the acceleration could be explained by radiation pressure from sunlight itself. For a naturally occurring rock, sunlight's push is far too weak to account for the observed effect. But if Oumuamua was extremely thin and light, like a sheet of material less than a millimeter thick, the pressure could work. This led to the startling speculation that Oumuamua could be a piece of alien technology, a discarded light sail from a distant civilization, drifting through the galaxy like cosmic litter. The scientific community largely rejected this as an extraordinary claim without extraordinary evidence, favoring natural explanations. Yet the core problem remained. A silent object with no visible exhaust was being pushed by something we could not see. Oumuamua forced astronomers to confront the limits of their categories. It was an asteroid-like object with comet-like behavior, but without the comet's telltale signs. It was a stranger that passed through too quickly, leaving behind only a trail of questions and a faint point of light fading into the eternal dark. The silence of its acceleration was the real puzzle. Without a visible trail of dust or gas, what invisible hand was giving Oumuamua that gentle push away from the sun? The most compelling natural answer lies in a substance we know well from our own solar system's frozen frontier: nitrogen ice. Picture the heart of Pluto, a world covered in vast glaciers of this pale, frozen gas. Now imagine a cataclysmic impact on a distant Pluto-like world in another star system. Such an event could have blasted a chunk of that nitrogen ice, perhaps hundreds of meters long, clear out into the void. This fragment, a cosmic iceberg, then drifted for millions of years before our solar system's gravity caught it. This nitrogen iceberg hypothesis elegantly solves the propulsion mystery. As Oumuamua approached the sun, the intense heat caused the solid nitrogen on its surface to sublimate, to turn directly from ice into gas without ever becoming a liquid. This streaming gas would act like a natural rocket engine, providing the precise non-gravitational push that Hubble detected. And because molecular nitrogen gas is very difficult for our telescopes to see, especially in such a tenuous stream from a small object, it would leave no visible coma or tail. The object's unusual shape, perhaps flattened like a cookie from eons of erosion, could also be explained by the way such ices sublimate unevenly in the vacuum of space. Yet for all its elegance, this theory demands a lot from the universe. Could a chunk of pure nitrogen ice really survive a multi-million-year journey through interstellar space, constantly bombarded by cosmic rays and starlight? And are such violent, fragmenting impacts on distant dwarf planets common enough for us to have encountered a piece of one so soon after beginning our search? These questions do not have easy answers. They highlight how Oumuamua, in its brief flyby, shattered our comfortable categories. It was not a standard comet nor a typical asteroid. It was something entirely new, a prototype for a class of object we had only theorized about, interstellar planetesimals, the building blocks of other solar systems arriving on our doorstep. Its greatest legacy is the permanent change it wrought on our perspective. Before Oumuamua, interstellar visitors were a theoretical footnote. Now we know they are passing through constantly, and our telescopes are actively hunting for the next one. Each new discovery will help us map the diversity of materials that exist between the stars. So while the nitrogen iceberg may be the best answer we have for now, the true resolution to the mystery is this: Oumuamua forced us to expand our imagination. It proved the galaxy is not just full of stars and planets, but of strange, silent travelers made of substances and shaped by processes we are only beginning to understand. The silent travelers between stars are shaped by forces within their own systems. But what if the entire cosmos, every galaxy cluster we can see, is being pulled by something from beyond the horizon of our reality? This is the terrifying proposition of the dark flow. After mapping the Great Attractor and our home supercluster Laniakea, scientists believed they had accounted for the largest gravitational movements in our universe. But data from the Wilkinson Microwave Anisotropy Probe, or WMAP, revealed something that should not exist. It suggested that hundreds of massive galaxy clusters, each containing thousands of galaxies, were all streaming in the same direction at staggering speeds of nearly 2 million miles per hour. This was not a local river of galaxies like the flow into Laniakea. This was a continental drift of the entire observable cosmos, as if some unimaginable mass beyond the edge of everything was reeling us in. To detect this, scientists used a subtle but powerful cosmic fingerprint called the kinetic Sunyaev-Zeldovich effect. Here is how it works. The cosmic microwave background, that faint afterglow of the Big Bang, fills the entire universe. When the hot gas that permeates giant galaxy clusters moves through this radiation field, it scatters the microwave photons and imprints a tiny, specific distortion on them. It is like hearing the faint Doppler shift in the sound of a passing train, but applied to the oldest light in existence. By meticulously measuring this effect in hundreds of clusters, the WMAP team could trace not just that they were moving, but the direction of their motion. The result was a coherent flow on a scale of billions of light-years, all pointing toward a specific patch of sky in the constellations Centaurus and Vela. This defied a foundational principle of cosmology, the cosmological principle, which states that on the largest scales, the universe should be homogeneous and isotropic. There should be no special direction, no grand up or down. The dark flow suggested there was a profound down, a gravitational slope so vast its source lay outside what we can possibly see. The implications were, and remain, revolutionary. If the flow is real, its source must be colossal, with a gravitational pull that dominates even the Shapley supercluster. But because it aligns with a direction, not a point source we can identify, the leading theory is that it originates from something beyond our cosmic horizon. Our observable universe is a bubble about 93 billion light-years across, limited by the distance light has had time to travel since the Big Bang. The source of the dark flow could be a concentration of mass so immense it formed in a neighboring region of space-time during the universe's inflationary period, a region that inflated into its own bubble universe, forever separate from ours but close enough that its gravity still leaks through the barrier, tugging on everything within our sight. It is a ghost from another cosmos pulling on the fabric of our own. Unsurprisingly, such an extraordinary claim has faced intense scrutiny. Later data from the Planck satellite, a more advanced mission, failed to confirm the signal with the same strength, though some researchers argue the analysis methods differed and the mystery persists. Whether a statistical fluke or a crack in our understanding of reality, the dark flow forces us to confront the most humbling possibility of all, that the grand structures we map may only be local scenery, and the true shape of existence extends into realms we can never directly observe. That claim of a continental drift of galaxy clusters was from the very beginning a declaration of war on standard cosmology. Extraordinary claims demand extraordinary evidence, and the scientific community responded with a barrage of rigorous skepticism. The first line of attack focused on the data itself. Critics argued that the subtle signal of the dark flow could be contaminated by systematic errors in the Wilkinson microwave anisotropy probe's instruments, or by incomplete modeling of foreground emissions from within our own galaxy. The cosmic microwave background is a whisper, and detecting the kinetic Sunyaev-Zeldovich effect within it is like trying to hear a single instrument tuning in a roaring symphony hall. Any misstep in subtracting the roar of our own Milky Way or the hum of local dust could create a phantom signal, a pattern in the noise that looks like motion but is just an artifact of our imperfect cleaning process. Others pointed to local gravitational influences. Could the combined pull of known superclusters like Shapley be somehow imitating a coherent flow on such vast scales? The debate raged in journals and conferences, a high-stakes statistical duel over the universe's largest possible motion. The decisive test would come from a more powerful instrument. The Planck satellite, launched by the European Space Agency, was the successor to WMAP, equipped with far greater sensitivity and resolution. The cosmology world waited for its verdict. When the Planck team analyzed their data for evidence of the dark flow, they did not see it, at least not with the same dramatic clarity and statistical strength. Their results suggested that any bulk flow of galaxy clusters was consistent with what could be generated by the known distribution of matter in the observable universe. There was no need to invoke a gravitational phantom from beyond the horizon. For many, this settled the issue. The dark flow was likely a compelling statistical fluke, a case of seeing a pattern in the cosmic static where none truly existed. Yet, like a stubborn ghost, the idea refuses to fully vanish. A subset of researchers, including the original team, maintain that when you analyze the data in a specific way, a residual signal persists. They argue for a bulk flow that is still larger than our best cosmological simulations predict, even if it is not the universe-spanning river first proposed. This lingering discrepancy, this whisper of excess motion, keeps the door to the extraordinary slightly ajar. It touches on the most profound questions we can ask. If the flow is real, even in a diminished form, its source must be something of almost inconceivable scale, something whose gravity dominates over everything we can see. The most mind-bending explanation is that we are feeling the tidal pull of a region of space-time that inflated into a separate universe during the Big Bang, a cosmic neighbor forever hidden beyond our observational horizon but close enough that its mass warps our local fabric of reality. It is the ultimate outsider, a ghost from another creation gently tugging at our own. For now, the dark flow remains in a purgatory of potential. It is an unconfirmed anomaly, a tantalizing maybe written in the oldest light in the universe. Its legacy is not a definitive discovery but a permanent question. It forces us to look at the maps of our cosmos and wonder if they are complete, or if we are merely charting the interior of a vast room, unaware of the colossal landscape just outside its walls. The colossal pull of the dark flow is a question written across the cosmos, but the deepest mysteries often hide in the smallest of spaces, within the collisions of particles smaller than atoms. In 2016, deep underground in a tunnel beneath the French-Swiss border, the world's most powerful microscope, the Large Hadron Collider, recorded a tiny, tantalizing blip. Within the compact muon solenoid experiment, one of the colossal detectors built to catch the debris of proton collisions, physicists noticed a slight excess in their data. Among the trillions of collisions, there were just a few more pairs of high-energy photons, particles of light, than their models predicted. This alone was not unusual. Statistical noise is common. But these photon pairs had a peculiar signature, a combined mass of around 750 giga-electron-volts. This specific energy bump, this tiny hill in an otherwise smooth landscape of data, was the hint of something new. In particle physics, such a resonance can be the fingerprint of a new, undiscovered particle. The excitement was immediate and electric. Could this be the next great discovery after the Higgs boson? The Standard Model of particle physics, our most successful theory of the fundamental forces in particles, has no particle that decays into two photons at that mass. This bump was an uninvited guest at the most precise party in science. Theorists around the world scrambled to their chalkboards. The most straightforward explanation was a new, heavier cousin of the Higgs boson, perhaps a sign of the mysterious supersymmetry that many physicists have long sought. Others proposed something even more revolutionary, a particle linked to gravity itself, a graviton, making its presence known. But the most exotic ideas ventured into truly uncharted territory. Some suggested the signal could be evidence of unparticles. This is not a typo. Unparticle physics is a theoretical framework proposing a hidden sector of reality that does not behave like the discrete particles we know. Normal particles have specific masses and follow predictable quantum rules. Unparticles, in contrast, would have scale-invariant properties, meaning they would look the same at all energy levels, more like a continuous, fluid substance than a distinct bullet. If such a thing existed and interacted with our familiar particles, it could produce unusual signals like an excess of photon pairs at a specific energy without looking like any known particle decay. The 750 GeV bump fit the profile for such a strange possibility. For months, the physics community buzzed with a feverish intensity. Hundreds of academic papers were written, each constructing elaborate models to explain the anomaly. Careers were momentarily redirected, conference agendas were written, all orbiting this tiny, unconfirmed excess in a data plot. It was a beautiful example of science in action, a collective sprint toward a potential new horizon. But the Large Hadron Collider is a relentless machine. It does not deal in speculation, only in cold, hard statistics. As the LHC collected more data in its next run, with more collisions and greater precision, physicists looked again. The bump, that hopeful hill, began to flatten. The extra photon pairs that had sparked 1,000 theories faded back into the background noise. By 2018, with the full dataset analyzed, the consensus was clear. The 750 GeV anomaly was a statistical fluctuation, a cosmic mirage in the desert of data. There was no new particle, no graviton, no unparticle. The Standard Model, triumphant once more, had not been cracked. Yet to dismiss this as a failure is to miss the point entirely. The episode was a vital fire drill. It showed the incredible sensitivity of our instruments, capable of spotting a whisper that makes an entire field hold its breath. It demonstrated the vibrant, responsive nature of theoretical physics, ready to leap at the slightest hint of something new. And most importantly, it reinforced a humbling truth. The universe guards its deepest secrets closely, and even our mightiest machines must sometimes answer with a patient, unwavering no. That fleeting whisper in the data was a powerful lesson in cosmic patience. The disappearance of the 750 giga-electron volt bump was not a failure of the instruments or the scientists, but a triumph of the scientific method itself. In high-energy physics, discovery is not a single eureka, a moment. It is a slow, meticulous siege against uncertainty. The initial excitement was the essential spark, the fuel that drives the entire machine forward. It mobilized theorists to stretch the boundaries of imagination, exploring wild and wonderful possibilities from extraspatial dimensions curled up smaller than an atom, to entire hidden sectors of dark matter particles communicating through forces we cannot feel. For a few thrilling months, the entire field lived in a world of what if, and that world was mapped in exquisite mathematical detail. That theoretical explosion had immense value, even though the specific signal faded. It refined our tools, exposed new connections between ideas, and left behind a richer landscape of possibilities for the next anomaly, the one that might be real. Then came the verification, the quiet, unglamorous work of collecting more data. The Large Hadron Collider is a statistical truth machine. It does not care about our hopes or our elegant equations. It only answers questions with more collisions, more proton smashes, until the signal either rises from the noise like a mountain or melts back into the flat line of background chance. In this case, it melted, and that is how it should be. This cycle of excitement and rigorous disproof is the heartbeat of modern science. It protects us from seeing patterns in the clouds while keeping our senses razor sharp for the day a pattern refuses to fade. So the 750 giga-electron volt anomaly stands as a beautiful phantom, a case study in how we navigate the edge of knowledge. It reminds us that the path to a true revolution is paved with false alarms, each one a necessary drill that prepares us to recognize the real thing when it finally arrives. Tabby's star was not the only cosmic lantern flickering in strange ways. A much smaller, younger star catalogued as Epic 204376607-1 delivered a light show that was, in its own way, even more dramatic. This is a young M-dwarf, a small, cool star still in its cosmic infancy, surrounded by the swirling chaos of a protoplanetary disk where planets are struggling to form. During the Kepler Space Telescope's K2 mission, astronomers watched as this star's light did something unbelievable. Over the course of a single Earth day, its brightness plummeted by a staggering 80%. To put that in perspective, if our sun did that, noon would become a deep, starry twilight in a matter of hours. This was not a gradual fade or a series of complex dips. It was a single, terrifying plunge into near darkness, followed by a slow, uneven recovery over the next week. The light curve, the graph of its brightness over time, looks less like an astronomical observation and more like the readout from a cosmic cardiac arrest. Explaining a dip this deep and this brief is a monumental challenge. It requires something colossal to pass in front of the star, but that something must also be incredibly narrow, like a razor-thin screen, to block the light for such a short duration. The usual suspect, a planet, is completely inadequate. Even a Jupiter-sized world would only cause a dip of about 1%. This was 80 times deeper. So what could possibly cast such a vast yet fleeting shadow? One theory points back to the dusty chaos of the star's youth. Imagine its protoplanetary disk not as a smooth, flat dinner plate, but as a warped, lopsided ring tilted almost edge-on from our perspective. Within that disk, there could be immense, dense clumps of material planetesimals colliding, or vast clouds of gas and dust condensing. If one of these monstrous, irregular clumps drifted across our line of sight, it could create that sudden, extreme blockage. Another, more violent idea involves a catastrophic collision. Picture two protoplanets, each perhaps the size of Mars, smashing together in the star's orbital plane. The titanic impact would vaporize rock and metal, instantly blasting out an expanding cloud of superheated debris and vapor. For a brief period, this cloud could be large and opaque enough to eclipse the star almost entirely before it rapidly expanded, cooled, and dissipated into the surrounding disk. And yes, for a fleeting moment, the alien megastructure hypothesis flickered to life once more in online forums. Could this be a partially constructed Dyson swarm, a single colossal panel blotting out the star? But the star's extreme youth works powerfully against this. This system is a mere infant, only about 10 million years old. For context, when our Sun was that age, Earth was a molten hellscape, and life was over 4 billion years in the future. It is astronomically improbable that a technological civilization could arise and embark on stellar engineering in such a brief, violent period of a star system's formation. The natural, if apocalyptic, explanations are far more plausible. What makes Epoch 2043767 so important is that it proves Tabby's star is not a singular freak. It shows us that the universe is capable of producing staggeringly extreme dimming events through natural, if poorly understood, processes. These young, chaotic systems are cosmic laboratories of destruction and creation, where shadows as deep as night can be cast by the birth pangs of planets or by their violent, premature deaths. That 80% plunge into darkness points directly to the star's chaotic cradle. The most compelling explanation for Epoch 204376607's bizarre behavior lies not in alien engineering, but in the messy, violent nursery that surrounds it, its protoplanetary disk. This is a vast, swirling cloud of gas and dust, the raw material from which planets will eventually coalesce. But this disk is not a perfect, flat ring like Saturn's. Observations of other young stars suggest these disks can be warped, tilted, or pockmarked with immense, dense clumps of material. Imagine a gigantic, lopsided sombrero made of cosmic dust spinning wildly around the star. If our line of sight happens to be aligned with the edge of this warped inner disk, we would see the star through its thickest, dustiest rim. A single, dense knot of material within that rim, perhaps a region where dust is clumping together under its own gravity, could drift into our view. This clump, potentially larger than our entire solar system's inner planets combined, would be mostly transparent at its edges but incredibly opaque at its core. As it passed in front of the star, it could create that sudden, terrifying drop in light, a shadow so deep it nearly snuffed out the star from our perspective. The star's extreme youth, a mere 10 million years old, makes this scenario not just plausible but likely. At this age, the system is in a state of furious construction. Planets are not yet fully formed worlds. They are embryos within a dusty womb, constantly colliding, accreting, and stirring up colossal clouds of debris. An event like the one we witnessed might be the signature of a protoplanet's growth spurt, a time when it is voraciously sucking up material and shrouding itself in a temporary cocoon of dust. Or it could be the aftermath of a collision between two such embryonic worlds, a catastrophic event that instantly vaporized rock and ice into an opaque, expanding shroud. These events are likely common in the chaotic early lives of stars, but catching one is a matter of cosmic luck. They are incredibly brief, often lasting only a day or two, and they are not periodic. You have to be staring at the right patch of sky with an incredibly sensitive instrument at the exact moment the shadow falls. This is what makes Kepler's data so precious. It was a continuous, unblinking eye on thousands of stars, allowing us to capture these fleeting celestial tantrums. So, while we may have missed the alien megastructure, what we gained is arguably more profound. Anomalies like this give us a front-row seat to the most fundamental process in cosmic construction. We are watching, in real time, the violent and messy birth of planets, a process where dust clouds the size of solar systems can eclipse their own suns in a celestial blink. It is a humbling reminder that our own serene solar system was once a similar maelstrom of shadow and light, a place where the building blocks of Earth were forged in darkness before settling into the stable orbits we know today. The violent construction zones of young stars are cloaked in dust, a perfect hiding place for cosmic newborns. But when the Spitzer Space Telescope peered into these stellar nurseries with its infrared eyes, it found something stranger than expected. Nestled within clouds like NGC 1333, astronomers spotted deep red smudges glowing with an unusual warmth. These were not the bright points of mature stars or the wispy filaments of gas. They were designated unidentified infrared objects, or UIROS, and they represented a new class of cosmic mystery. Their defining trait was their invisibility. In ordinary optical light, these regions of space appeared as empty, cold darkness, but in the infrared spectrum they shone with a distinct, ruddy glow. This told scientists one thing immediately: these objects were buried. They were deeply embedded within thick, cold cocoons of cosmic dust, so completely shrouded that even their heat signature was muffled and distorted. What could possibly be glowing inside such a dense blanket? The leading theories point to the earliest, most secretive stages of stellar birth. A star begins not as a shining sphere, but as a collapsing knot within a cold molecular cloud. As gravity pulls the material inward, it heats up, but for a long time, all that heat is trapped by the infalling dust. This creates what astronomers call a Class 0 protostar. It is an object with a hot, dense core, but it is not yet fusing hydrogen. It is a star in its fetal stage, powered solely by the gravitational energy of its own collapse. A UIRO could be one of these embryonic suns, so young and so deeply buried that it has never been seen before in such clear infrared isolation. Its distinctive red glow would be the thermal radiation from its warm dust cocoon, the only sign of the violent birth happening within. Another possibility is even more intriguing. Perhaps these are not stars at all, but failed stars. Brown dwarfs are objects too massive to be planets, yet not massive enough to ignite sustained nuclear fusion in their cores. They form like stars from collapsing clouds, but they end up as dim, cool embers. A very young brown dwarf, still swaddled in its dusty natal material, could also produce the isolated, red infrared signature of a UIRO. This would make them crucial missing links, helping us understand the blurry line between the smallest stars and the largest planets. The mystery deepens because these objects are not just faint, their infrared colors are peculiarly red, suggesting the dust around them has unique properties, perhaps grains of a different size or composition than usual. Are we seeing a special, fleeting phase of development that most objects pass through quickly? Or is this a sign of an entirely different formation process? For now, these unidentified red smudges remain cryptic birth announcements from the darkest corners of star-forming clouds, silent clues to how both suns and their dimmer cousins first step into the light. Those deep red smudges are more than just infrared curiosities. They are potential windows into the universe's first nursery. Unidentified infrared objects could be cosmic infants caught in their first moments of gravitational awakening, a phase so brief and hidden it has remained largely theoretical. After a dense knot within a molecular cloud begins to collapse under its own weight, it enters a critical period known as the Class 0 protostellar stage. For perhaps just 100,000 years, a mere blink in cosmic time, the object is powered not by nuclear fusion, but by the raw, violent energy of infall. As gas and dust rain down onto the core, they compress and heat up, but all that warmth is trapped by the very material still falling in. The result is a warm, deeply buried ember, glowing a dull red in the infrared, precisely the signature of a UIRO. This makes them the missing link between cold, dark clouds of potential and the brilliant, fusion-powered stars that light up galaxies. By studying their faint light, astronomers are not just looking at an object, they are reading the opening chapter of a star's biography, written in the heat of collapse and the chemistry of pristine dust. The significance of this goes beyond simply cataloging another stage of stellar evolution. The light from a URO carries a forensic record of its environment. Through a technique called spectroscopy, scientists can split that faint infrared glow into a rainbow of colors, revealing dark lines and bright bands that act as chemical barcodes. Each element and molecule absorbs or emits light at very specific wavelengths. By analyzing the spectrum of a URO, researchers can determine the composition of the dust cocoon shrouding it. Are there complex organic molecules, the precursors to the building blocks of life, already forming in this frigid, dense environment? What is the mix of ices, water, ammonia, methane that coat the dust grains? This information is a direct snapshot of the raw materials from which an entire planetary system will one day be built. It tells us what chemistry was present in the solar nebula before planets ever began to coalesce, offering clues to the initial conditions that led to worlds like our own. In this way, a URO is not just a baby star, it is a sealed time capsule containing the recipe for its future family of planets. For decades, these objects have been little more than enigmatic red blurs, their secrets locked behind thick veils. That is about to change completely. The James Webb Space Telescope, with its gold-coated mirrors and suite of infrared instruments, was built for this exact mystery. Its supreme sensitivity allows it to peer through obscuring dust with unprecedented clarity, and its spectroscopic capabilities can dissect the light from these faint objects in exquisite detail. Where Spitzer saw a smudge, Webb is poised to reveal intricate structure. It may resolve a URO into a distinct pinprick core surrounded by a swirling, flattened disk of material, the protoplanetary disk in its absolute infancy. It could detect the faint, bipolar jets of material that often erupt from the poles of a young stellar object, a sign of the violent dynamics of accretion. Most importantly, Webb's powerful spectrographs will read those chemical barcodes with a precision never before possible, identifying not just the presence of molecules, but their abundances and even their temperatures. This data will transform URO from unidentified anomalies into well-characterized laboratories, allowing us to test our models of how stars and planets are born against the hard evidence of reality. The very existence of URO and our struggle to define them carries a profound lesson about cosmic discovery. They remind us that even in the most well-studied stellar nurseries, photographed countless times by powerful telescopes, entirely new classes of objects can still be hiding in plain sight, or rather in plain darkness. Their discovery tells us that our maps of the cosmos are still incomplete, not just at its edges but in its most fundamental processes. Every thick veil of dust, once an impenetrable barrier, becomes a promise with the right tools. It suggests that the universe still holds basic, formative stages of existence that we have yet to witness directly, phases of creation that occur in silence and shadow before anything shines in visible light. As Webb and future observatories turn their gaze toward these infrared riddles, we stand on the verge of watching the universe write its own first words, in the warm glow of dust and the silent collapse of gravity. Deep within the dusty lanes of our own galaxy, a new kind of heartbeat began to pulse. In January 2022, astronomers sifting through data from the Murchison Widefield Array in the remote Australian outback found a signal so strange it defied every known category of cosmic object. Catalogued with the cumbersome name Gleam XJ16275 9.552350.4.3, this source, a mere 4,000 light-years away, was broadcasting a message of pure rhythmic power. Every 18.18 minutes, with a precision rivaling an atomic clock, it would erupt. For 30 to 60 seconds, it became one of the brightest radio sources in the entire sky, a brilliant flash of highly polarized waves. Then it would vanish back into silence, only to return exactly when predicted. This was not the frantic, millisecond ticking of a pulsar, the spinning corpse of a massive star. It was a slow, stately, and monstrously powerful drumbeat echoing from the void. The pulses themselves held a crucial clue. Their light was polarized, meaning the radio waves were all aligned, vibrating in the same plane. This is the signature of an immensely strong and ordered magnetic field, a cosmic lighthouse where the beam is sculpted by magnetic forces of almost unimaginable intensity. So what kind of object could possibly produce such a slow, yet incredibly luminous and structured signal? The first, most obvious suspect was a magnetar, the most magnetic star in the universe. But there was a profound problem with that idea. Magnetars, like all neutron stars, are tiny and incredibly dense, spinning on their axes in a matter of seconds, not minutes. For a magnetar to have an 18-minute spin period, it would have to be spinning impossibly slowly, which would require it to have been born with virtually no rotational energy, or to have been braked by a mechanism beyond anything we understand. It was like finding a hummingbird with the wing beat of an eagle. It simply did not fit the known physics of these objects. This led theorists to a fascinating and rare alternative, a white dwarf pulsar. White dwarfs are the Earth-sized cores of dead, sun-like stars. They are much larger and less dense than neutron stars. If a white dwarf possessed a magnetic field 1,000,000 times stronger than Earth's, but 100 times weaker than a magnetar's, it could, in theory, produce coherent radio beams from its magnetic poles. Because it is larger, it would rotate more slowly, making an 18-minute period plausible. We have only confirmed one other object like this in our galaxy, proving such things exist, but they are exceptionally rare cosmic beasts. Yet, even this compelling explanation faces challenges. The sheer brightness of the pulses from Gleam XJ 16275-9.5 is staggering for a white dwarf. It demands an engine of extraordinary efficiency, pushing the limits of what such an object is thought capable of. For now, this enigmatic beacon remains a profound puzzle in our own galactic neighborhood, a slow, bright metronome ticking in the dark, forcing us to expand our catalogue of what is possible when a star dies and leaves behind a magnetic ghost. That slow, bright metronome from Gleam XJ 16275-9.5 forces us to rewrite the textbook on dead stars. The leading hypothesis points to something extraordinary, the first confirmed white dwarf pulsar. To understand why this is revolutionary, picture the quiet fate of most stars like our Sun. After burning through their fuel, they shed their outer layers, leaving behind a dense, Earth-sized core of carbon and oxygen, a white dwarf. It is a fading ember, slowly cooling over billions of years. We have never seen one pulse like a lighthouse, but this object suggests a white dwarf can have a second act, a dramatic one. Imagine taking that fading ember and giving it two monstrous attributes: a spin of terrifying speed for its size, and a magnetic field 1,000,000 times stronger than Earth's, though 100 times weaker than a magnetar's. This combination could forge a cosmic engine. As the white dwarf spins, its immense magnetic field channels charged particles toward its poles, accelerating them to near light speed. Where these particles slam into the surrounding space, they generate intense beams of coherent radio waves, flashing toward us with each rotation. An 18-minute spin period, impossible for a tiny neutron star, becomes perfectly plausible for this larger, more massive object. It is a slower, grander clockwork, a celestial beacon built from different materials. Confirming this would rip open a new chapter in stellar evolution. We have always classified pulsars as the exclusive domain of neutron stars, the remnants of violent supernova explosions. A white dwarf pulsar would prove that gentler stellar deaths can also produce powerful, organized radiation if the conditions are just right. It tells us that magnetic personality is not reserved for the most violent corpses. The search is now frantic. Astronomers are scouring archival data and directing new observations, hunting for other slow-pulsing radio sources. Each new detection would help map the bizarre zoo of magnetic dead stars, revealing how common these slow-ticking giants might be. The mystery of that 18-minute pulse, therefore, is more than a solved puzzle. It is a landmark. It drove home a humbling and thrilling truth. Even with our sky mapped in countless wavelengths, our own galaxy remains a place of fundamental surprise, capable of conjuring entirely new classes of objects from the ashes of familiar stars. That slow-ticking beacon forces us to rewrite the rules for dead stars, but the universe's greatest shortages are not about rare objects. They are about missing ingredients from the very recipe of creation itself. We have a precise cosmic cookbook written in the first few minutes after the Big Bang. From the primordial nuclear fusion of that hot, dense beginning, a process called Big Bang nucleosynthesis, we can calculate exactly how much ordinary matter should exist today. Ordinary matter, the stuff of stars, planets, and us, is known as baryonic matter made of protons and neutrons. The math is elegant and has survived every test. Yet, when astronomers add up all the ordinary matter, they can see every galaxy, every star, every wisp of glowing gas in space, they come up staggeringly short. Roughly half of all the baryonic matter the universe is supposed to contain is simply missing. This is not dark matter, that mysterious, invisible substance that outweighs normal matter 5 to 1. This is the regular atoms we are made of, and half of them have vanished from our inventory. The problem is not that this matter is inherently dark or invisible. It should interact with light in some way we can detect, whether by glowing, reflecting, or absorbing it. So where did it go? The leading theory points to the grandest structures in the cosmos, the cosmic web. Between the brilliant knots of galaxies and clusters stretch immense, thread-like filaments of gas, spanning hundreds of millions of light-years. Theorists believe the missing half of all atoms is hiding there in the form of a searing, incredibly diffuse fog known as the warm-hot intergalactic medium, or WIM. This is gas heated to temperatures between 100,000 and 10 million degrees, so hot it is ionized, meaning its electrons have been stripped from its atoms. At these temperatures, it does not glow in visible light. Instead, it emits only the faintest whisper of X-ray radiation, a whisper so soft it drowns in the background noise of the universe. Detecting it is like trying to hear a single conversation in a roaring sports stadium from a mile away. Astronomers have had to become cosmic detectives, looking for clues not in what the WIM emits but in what it steals. When the brilliant light of a distant quasar, a galaxy with a voracious black hole at its heart, travels across the universe toward us, it passes through these invisible filaments. The superheated gas in the WIM can absorb specific, telltale wavelengths of that quasar's ultraviolet light. By studying the quasar's spectrum, the detailed fingerprint of its light split into a rainbow, scientists can search for the faint, dark lines where the WIM has taken a bite. It is painstaking work, requiring perfect alignments between distant quasars and suspected filaments, and the signatures are incredibly subtle, but slowly, piece by piece, evidence has mounted. Observations from space telescopes like Hubble and XMM Newton have begun to find these absorption lines and even detect the faint X-ray glow from the densest knots of this intergalactic fog. The case is not yet closed. We have not accounted for every last missing atom, but the trail is growing warmer. The mystery of the missing baryons, therefore, transforms our view of the cosmos. It reveals that the universe does not waste its building blocks. They are not lost, they are simply hidden in plain sight, woven into the invisible scaffolding that holds galaxies together. The vast spaces we once thought of as empty are, in fact, an ocean of million-degree gas, a hidden reservoir containing half of all normal matter. Finding it all is the ultimate cosmic accounting challenge, proving that even the most fundamental ingredients of reality can hide in the spaces between everything we see. Finding those missing atoms is a detective story written in the faintest ink. To hunt the warm, hot intergalactic medium, astronomers must become masters of cosmic forensics, looking not for what the whim emits but for what it steals. Their primary tool is the brilliant, distant quasar. These are galactic cores powered by supermassive black holes, shining with the light of 1 trillion suns. As that intense beam of ultraviolet light travels billions of light years to reach us, it passes through the invisible filaments of the cosmic web. When it slices through a strand of the whim, the superheated gas leaves a fingerprint. Highly charged atoms of oxygen, like oxygen-7 and oxygen-8, absorb very specific, precise wavelengths of that quasar light. By splitting the quasar's light into a rainbow spectrum, scientists can search for the tiny, dark lines at those exact wavelengths. Finding them is like finding a specific person's fingerprint on a bullet fired across a continent. It proves that person, or in this case, that specific gas, was in the path. This method has provided the first solid evidence that the whim exists, but it is painstaking. It requires a quasar perfectly aligned behind a suspected filament, and the signal is incredibly weak, often buried in noise. A second, more direct approach is to try and see the whim's own faint glow. At millions of degrees, the gas should emit soft X-rays. Telescopes like XMM Newton and Chandra have spent countless hours staring at the spaces between galaxies, searching for this diffuse X-ray haze. The signal is so faint it is often indistinguishable from the X-ray background of the entire universe, like trying to see a single candle's glow through a dense, distant fog. To amplify the signal, astronomers have turned to a different cosmic effect, the same one used to detect the dark flow, the Sunyaev-Zeldovich effect. This time, they apply it to the filaments connecting galaxy clusters. As the faint microwave background radiation passes through the hot electrons in these filaments, the electrons give the photons a tiny energy boost. By mapping this subtle distortion in the microwave background around pairs of clusters, scientists can infer the presence and density of the hot gas bridging them. It is a way to weigh the invisible, to trace the outline of the cosmic web's arteries with the oldest light in existence. This hunt is about to leap forward with a new generation of instruments. The upcoming X-ray Imaging and Spectroscopy mission, XRISM, and the future Athena Observatory are being engineered with this specific mystery in mind. Their advanced X-ray spectrometers will have the resolution to not just detect the whim glow, but to measure its temperature, density, and motion in exquisite detail. They will be able to dissect the absorption lines from quasars with unprecedented precision, turning faint hints into definitive measurements. Solving the missing baryon anomaly is not an academic exercise. It is the final audit of the ordinary universe. If we can account for every atom predicted by the Big Bang, it powerfully validates our entire standard model of cosmology. If we cannot, it means something fundamental is wrong with our understanding of how matter is distributed, or perhaps even how the early universe behaved. The quest transforms those vast, empty spaces between galaxies into a frontier, a hidden ocean we are just learning to sail, its waters holding the answer to a question as old as creation itself. Is our cosmic ledger finally balanced? Our cosmic ledger may one day be balanced, but some entries in its inventory challenge the very nature of reality itself. Long before black holes became a staple of textbooks and science fiction, their theoretical possibility sparked a fierce debate. Einstein's equations of general relativity clearly predicted points of infinite density, singularities, but many physicists found the idea philosophically troubling. What if, they asked, nature found a way to avoid such a monstrous endpoint? One compelling alternative emerged: the dark energy star. Proposed by physicist George Chapline, this theoretical object offers a radically different fate for a collapsing star. Imagine a massive star reaching the end of its life, its core succumbing to gravity. In the traditional black hole model, it collapses forever, crushing itself into a dimensionless point of infinite density. The dark energy star model suggests a salvation at the final moment. As matter is compressed beyond a critical threshold, it undergoes a profound phase transition, like water freezing into ice but far more exotic. The ordinary matter of the star's core is transformed into dark energy, the same mysterious repulsive force that is accelerating the expansion of the entire universe. This creates an interior with intense negative pressure, a kind of cosmic cushion that pushes outward with enough force to exactly counterbalance the inward crush of gravity. The collapse stops. There is no singularity, only a dense, dark energy-filled core. From the outside, however, the difference is nearly impossible to spot. The object would still possess an event horizon-like surface, a point of no return for light and matter. Anything crossing that boundary would be trapped not by a singularity, but within the exotic dark energy interior. To a distant astronomer, it would look, weigh, and gravitate almost exactly like a black hole. So if they behave identically, how could we ever tell the difference? The anomaly lies in the subtle signatures. A dark energy star might evaporate differently. Stephen Hawking predicted that black holes slowly leak radiation and evaporate over astronomical timescales. A dark energy star, through a process called quantum criticality, could potentially decay in a distinct manner, perhaps leaving behind a remnant or releasing a different spectrum of particles. Another clue could come from the final moments of matter falling in. As material approaches the boundary of a true black hole, it is thought to be ripped apart by tidal forces and lost forever to the singularity. In a dark energy star, that infalling matter might interact with the repulsive dark energy core in a way that produces faint, specific signals, perhaps bursts of particles or unusual radiation, before being incorporated into the star's interior. For now, every object we call a black hole, from Cygnus X1 to the monster at the center of our galaxy, remains a candidate for this stranger identity. The dark energy star is a beautiful reminder that our universe's most terrifying phenomena might yet hide a core of profound mystery, a secret engine of cosmic expansion locked inside the darkest of prisons. That dark energy prison, if it exists, would leave subtle cracks in its facade. The most profound difference between a black hole and a dark energy star lies at its boundary, the event horizon. For a classic black hole, this is a point of no return, a one-way membrane where space-time folds in on itself. Nothing, not even light, can escape once it crosses. A dark energy star, however, might not possess this absolute barrier. Its repulsive dark energy core could create a surface that is incredibly dense and light-trapping, but not perfectly so. Information, in the form of quantum particles or faint radiation, might have a pathway to leak back out into the universe over time. This difference could be imprinted on the most violent events we can now detect, the collisions of these monstrous objects. When two black holes spiral together and merge, they create gravitational waves, ripples in space-time. The final moments of this merger, called the ring-down phase, are like the ringing of a bell. The frequency and decay of this ringing are determined by the properties of the final object, its mass, spin, and crucially, the nature of its surface. A perfect event horizon rings one way. A dark energy star surface with its different quantum properties might ring with a slightly different tone or dampen the vibrations more quickly. Our gravitational wave observatories, LIGO and Virgo, are listening to these cosmic bells with ever-increasing precision. While current data perfectly matches predictions for black holes' future, more sensitive detectors could potentially hear the subtle discordant note that reveals a different interior. Another test looks at the fiery banquet of matter these objects consume. As gas spirals into a black hole, it forms a superheated accretion disk, a whirlpool of plasma that glows brilliantly in X-rays. The dynamics of this plasma are governed by the intense gravity right at the precipice of the event horizon. A dark energy star with its repulsive core could alter the magnetic fields or the turbulence in that final plunge, creating a different pattern of X-ray flickering or a distinct shadow in the radio wavelengths observed by the Event Horizon Telescope. These are not easy measurements. They require separating the signal of new physics from the complex, chaotic astrophysics of hot gas and magnetic fields. For now, every observation of Cygnus X1, of the black hole at our galaxy's heart, and of merging gravitational wave sources aligns beautifully with Einstein's predictions for classic black holes. The dark energy star remains a fascinating thought experiment, a ghost in the equations, yet its value is immense. It forces us to ask not just what we see, but what we assume. It connects the fate of a single star to the largest mystery in cosmology, dark energy itself, suggesting that the force accelerating the entire universe might also hide in the heart of its darkest objects. This speculative idea ensures that as we peer into the shadows of black holes, we remember to question the very nature of the darkness we find. This perfect symmetry between a world and its moon is a cosmic ballet of mutual respect. While our own moon is tidally locked to Earth, always showing us its familiar face as we spin freely, the Pluto-Charon system performs a different dance entirely. They are locked in a mutual synchronous rotation, a gravitational embrace so complete they are forever facing one another. Picture two dancers holding hands and spinning around a point between them, never breaking eye contact. That point is their common center of mass or barycenter, and it does not lie inside Pluto. Because Charon is so massive, about 1/8 the mass of Pluto itself, the barycenter hangs in the empty space between the two bodies. They orbit this invisible point like a cosmic dumbbell, a true binary system. In many ways, they are less a planet and moon and more a double dwarf planet, a pair of frozen worlds waltzing through the Kuiper Belt's dark. This perfect lock is the real mystery. Tidal locking is a natural process, a gravitational braking system. A larger body's gravity creates a bulge on its smaller companion. As the companion spins, this bulge tries to stay aligned, creating friction that slowly drains its rotational energy until its spin matches its orbital period. Our moon achieved this billions of years ago, but for both bodies in a pair to be locked is exceptionally rare, especially for a system so small and so far from the Sun. The Earth will never become tidally locked to the Moon. Our planet is too massive, its rotation too energetic. For Pluto and Charon to have both surrendered their independent spins suggests a history of profound violence and rapid change. The leading theory begins with a cataclysm. Early in the solar system's history, a primordial Pluto was likely struck a glancing blow by another large Kuiper Belt object. This colossal impact blasted material into orbit around Pluto, which then coalesced under its own gravity to form Charon. Initially, both worlds would have been spinning wildly and their orbits chaotic. But here, in the cold quiet of the outer solar system, a powerful engine went to work: tidal friction. The gravitational pull between the two newborn bodies, combined with the likely presence of a subsurface ocean on Pluto in its warmer past, created immense internal heat from the constant flexing and stretching. This tidal heating acted as a cosmic brake, sapping their rotational energy at a remarkably fast pace. Within perhaps just a few million years, a blink in geological time, their frantic spins settled into the serene, face-to-face lock we see today. Their dance is a frozen record of that ancient violence, a testament to how even the coldest, most distant worlds can bear the warm scars of a fiery birth. That ancient impact did more than just forge a moon. The colossal collision that birthed Charon was a defining event for the entire Pluto system, a shockwave that set in motion a chain of cosmic consequences we can still read today. The leading theory suggests a world roughly the size of Pluto, often called Proto-Pluto, was struck a glancing blow by another massive body early in the solar system's history. This was not a gentle merger, but a violent, off-center smash that vaporized and ejected a vast amount of material from the impactor and Pluto's own mantle. Much of this debris was flung into space, but a significant portion remained in orbit, a seething, hot ring of rock and ice. Within this chaotic disk, the largest fragments quickly began to coalesce, their gravity pulling in smaller pieces until a dominant body emerged, Charon. This giant impact model is our solar system's origin story writ small, a direct parallel to the event that formed our own moon from a young Earth, but the story did not end with the debris settling. The newborn Charon was likely in a much tighter, chaotic orbit around a still spinning, wounded Pluto. Here, gravity's most patient force took over, tides. The gravitational pull of each body creates a bulge on the other. As they spun and orbited, these bulges were constantly being pulled out of alignment, creating immense internal friction. This tidal friction acts as a cosmic brake, relentlessly sapping rotational energy and transferring it into heat and orbital momentum. Over millions of years, this process did two profound things. First, it dramatically expanded Charon's orbit, pushing the moon outward to its current distance. Second, it slowed the rotations of both bodies until they became perfectly synchronized, forever facing one another in that elegant gravitational lock. This dance was not serene, it was powered by deep internal warming. Data from the New Horizons flyby in 2015 revealed stunning, unexpected geology on both worlds, vast, uncratered plains of frozen nitrogen on Pluto and a giant, reddish polar cap on Charon. These features point to geologically active pasts with resurfacing and possible cryovolcanism. The most likely engine for that activity was the heat generated by their tidal tug of war. In fact, scientists now suspect both Pluto and Charon may have hosted subsurface oceans of liquid water in their early histories, kept warm by the constant flexing of their crusts. This transforms the Pluto-Charon system from a simple pair of frozen rocks into a dynamic, evolved binary planet, shaped as much by internal warmth as by external cold. Their perfect lock, therefore, is not a static oddity. It is the frozen signature of a violent beginning and a thermally active youth. It shows us that even in the silent, sunless reaches of the Kuiper Belt, worlds are born from catastrophe and sculpted by the slow, relentless mathematics of gravity, leaving behind a balanced partnership that tells the story of its own creation. Pluto and Charon's perfect lock is a signature of youth, a system still echoing with the chaos of its formation. But that same formative chaos on a much grander scale is now revealing itself as a common, if bizarre, phase for infant suns. Tabby's star was our first glimpse of this celestial drama, but it is far from alone. Astronomers have since identified an entire class of Dipper stars, primarily young stellar objects still nestled within their dusty birth cocoons in regions like the Taurus molecular cloud. These stars behave like Tabby's fainter, more numerous siblings, flashing the same strange signal of deep, irregular dimming. The key difference lies in their environment and their glow. While Tabby's star is a mature, isolated sun, these Dippers are cosmic newborns, and they almost always show a strong infrared excess. That extra infrared warmth is the telltale heat signature of vast amounts of circumstellar dust, the raw material of planet formation swirling close to the star. This single clue transforms the mystery. It strongly suggests we are not looking at alien megastructures, but at the messy, natural architecture of stellar infancy. The leading explanation focuses on the protoplanetary disk itself. Instead of a smooth, flat ring, imagine a disk that is dramatically warped, or one filled with colossal, dense clumps of material. As these stars spin, these warps and clumps, some larger than our entire solar system, rotate through our line of sight. When they do, they cast deep, fleeting shadows, blocking anywhere from a few % to over half of the star's light for days or weeks at a time. Other models invoke swarms of giant, icy planetesimals or comets, much like the early theories for Tabby's star, but on a scale that matches the violent construction zone of a young system. The true mystery now lies in the breathtaking variety of the dips themselves. No two Dipper stars are exactly alike. Some show symmetric V-shaped dips as if a solid-edged cloud passed by. Others have jagged, complex profiles with multiple minima, suggesting a shadow cast by a spiral arm within the disk or a swarm of several distinct fragments. There are dips with slow, sloping declines and sharp recoveries, and others that look like stair steps, as if a series of veils were being drawn aside. This menagerie of light curves points to a corresponding menagerie of structures within these disks, not just simple clumps but tendrils, arcs, and possibly even migrating protoplanets trailing immense shrouds of captured dust. Studying these Dipper stars does more than catalog curiosities. It provides essential context for the grand anomaly that started it all. They show that extreme, irregular dimming is a real, observable phase in the lives of some stars, particularly the young and dusty. This makes Tabby's star, a more mature star without the obvious infrared signature, even more intriguing. Was it once like these Dippers, and we are seeing the late-stage aftermath of that chaotic period? Or is its dimming driven by a completely different, rarer mechanism? The Dipper stars teach us that the universe has many tools to cast a shadow, and by learning to read their shapes, we are essentially decoding the blueprints of planetary systems under construction, watching as gravity sculpts dust into worlds, one deep, dark dip at a time. That precise viewing angle is everything. For a star to become a Dipper, we must be looking almost directly at the edge of its protoplanetary disk. From this side-on perspective, the disk appears as a thin, dark lane silhouetted against the star. Any structure within that lane, a dense knot of dust, a warped spiral arm, a migrating clump of material, will eclipse the star as it orbits by. It is a cosmic alignment that turns a distant star into a natural movie screen where the shadows of forming planets are cast in real time. The dips themselves are not simple blackouts. Detailed analysis of the starlight during an eclipse reveals a crucial fingerprint. The dimming is often more pronounced in blue light than in red. This color dependence is the definitive proof that the shadow-casting material is made of tiny dust grains, not solid objects. Small particles scatter shorter blue wavelengths more effectively, just like our own atmosphere scatters sunlight to create a blue sky. This tells astronomers they are witnessing the behavior of fine, micron-sized dust, the very stuff that will one day clump together into pebbles, then rocks, and finally planetary cores. By meticulously modeling the shape, depth, and duration of these complex light curves, researchers can perform a kind of astronomical tomography. They can infer the size, shape, and orbital distance of the obscuring cloud. A sharp, symmetrical dip might point to a compact, well-defined dust clump. A long, gradual decline with a jagged recovery could trace the silhouette of an extended spiral structure stirred up by a hidden, newborn planet's gravity. This transforms a puzzling anomaly into one of the most powerful diagnostic tools in astrophysics. We are no longer just watching stars flicker. We are using their light as a surgical probe to dissect the anatomy of infant solar systems. Each dip is an X-ray, revealing the hidden bones of a planetary nursery in the violent act of construction. It shows us a realm of incredible dynamism, where magnetic fields stir the dust, gravitational instabilities carve out lanes, and the gentle tug of unseen protoplanets sculpts the raw material of creation. In the flickering of these young stars, we witness the universe not as a static museum, but as a chaotic, bustling workshop where the shadows themselves tell the story of worlds being born. But what if a galaxy could be built almost entirely from the invisible? While NGC 1052DF2 shocked us with its lack of dark matter, another ghostly galaxy revealed the opposite, a truth just as unsettling. In the dense, violent Coma cluster, a cosmic metropolis of thousands of galaxies, astronomers found a wisp so faint it was nearly missed. They named it Dragonfly 44. Through the lens, it looked like a failed puff of smoke, a sparse collection of ancient stars so thinly spread you could see right through it to the universe beyond. Its stellar mass was a mere 1% of our Milky Way's, a pathetic glimmer in the grand scheme of things. Yet, when scientists measured the motions of its stars and globular clusters, they received a staggering surprise. Those faint points of light were whizzing around at tremendous speeds. The gravity required to hold this faint cloud together, to prevent its stars from simply flying off into the void, was colossal. The math was undeniable. Dragonfly 44, this faint, fluffy apparition, possessed a dark matter halo as massive as our entire Milky Way galaxy. Imagine a balloon the size of a city, but filled with nothing but a few grains of sand. Now imagine those few grains of sand somehow possessing the weight and gravitational pull of an entire mountain. That is the profound contradiction of Dragonfly 44. It is a cosmic paradox, a galaxy built from a ghostly skeleton with barely any visible flesh. This discovery sent a different kind of shockwave through astronomy. It proved that dark matter is not always neatly proportional to starlight. Here was a galaxy where the invisible scaffolding completely dominated, creating a gravitational giant masquerading as a faint dwarf. How does such a thing even form? One leading theory paints a picture of a cosmic failure. Perhaps Dragonfly 44 is a galaxy that never truly woke up. In the early universe, a vast cloud of dark matter collapsed, creating a deep gravitational well. But the normal gas that fell into that well, the fuel for star formation, was somehow stifled. Maybe it was heated by the intense radiation from nearby quasars in the crowded cluster, or perhaps supernova explosions from its first, feeble generation of stars blew the remaining gas away before more stars could ignite. The result is a dark matter fortress with only a tiny, sputtering stellar population, a failed city whose lights never fully came on. The other possibility is a story of cosmic violence. Dragonfly 44 may have once been a more normal, star-rich galaxy, similar to our own, but as it plunged into the crowded Coma cluster, it passed through the searing hot plasma that fills the space between galaxies. This intergalactic medium acts like a relentless sandblaster, stripping away a galaxy's star-forming gas in a process called ram pressure stripping. Over billions of years, this could have robbed the galaxy of its ability to make new stars, while leaving its immense dark matter halo untouched and its old, red stars in place. The galaxy was not born a ghost, it was slowly, methodically disemboweled, leaving behind a dark matter shell and a fading stellar memory. Dragonfly 44 and NGC 1052DF2 are two sides of the same confounding coin. One is missing its dark matter, the other is almost nothing but dark matter. Together, they scream that the recipe for a galaxy is far more complex and varied than our textbooks assumed. They force us to see dark matter not as a uniform ingredient, but as a substance that can, under the right conditions, be separated, isolated, or left to rule alone. In the faint glow of Dragonfly 44, we are not looking at a failed galaxy, but at a pure expression of the universe's hidden mass, a whisper of stars telling the story of the immense, silent darkness that holds them. That immense dark matter fortress, Dragonfly 44, forces us to rewrite the story of a galaxy's life. How does a cosmic structure with the gravitational might of the Milky Way end up with barely a flicker of starlight? The answer lies in the violent neighborhood it calls home, the Coma cluster. Imagine a galaxy, perhaps once a normal spiral, venturing too close to the cluster's dense, chaotic core. Here, it is not just passing other galaxies, it is swimming through a searing ocean of superheated plasma, millions of degrees hot, that fills the space between them. The galaxy's own reservoir of cool gas, the fuel for new stars, meets this intergalactic furnace. The result is a brutal stripping process called ram pressure. Think of driving a convertible through a torrential downpour at high speed. the rain does not just hit you, it forces its way in, soaking everything. In the Coma cluster, that plasma rain is so intense it can rip the star-forming gas right out of a galaxy's grasp. Over billions of years, this cosmic sandblaster can leave a galaxy gas poor and starved, unable to birth new suns. But the process might be even more violent. The immense gravitational tides from the cluster's core and from close encounters with other giant galaxies could physically tear stars away, pulling them out into long, faint streams. This is tidal stripping. Dragonfly 44 in this scenario is a galactic survivor, a remnant. It is the dark matter skeleton and the oldest, most tightly bound stars of a once grander spiral, everything else stripped away by the cluster's relentless violence. Its faint glow is the ghost of a galaxy that was, but there is another, equally compelling origin story. What if Dragonfly 44 was born a ghost? In this narrative, it never had a glorious, star-rich past. Instead, it formed in a peculiar pocket of the early universe. A vast cloud of dark matter collapsed, creating a deep gravitational well, just as expected. But when the normal, baryonic gas fell in to form stars, something went wrong. Perhaps the gas was preheated by the intense radiation from the first brilliant quasars, making it too turbulent to collapse easily. Or maybe the first generation of stars that did manage to form were so massive and explosive that their supernova blew the remaining gas clear out of the dark matter halo before more stars could ignite. This is called early feedback, a self-limiting process. The galaxy, in essence, choked on its own first breath. It became a cosmic failure, a dark matter palace built for a party that never truly began. This idea is supported by the galaxy's ancient red stellar population. Its stars are old and uniformly so, suggesting that whatever star formation happened, it occurred in a single, brief burst eons ago and then shut down forever. There is, however, one glaring clue that complicates both stories. Despite its pathetic stellar mass, Dragonfly 44 hosts a surprisingly rich family of globular clusters. These are dense, spherical swarms of up to 1 million ancient stars each. Our Milky Way has about 150 of them. For a galaxy as faint as Dragonfly 44 to have a similar number is bizarre. It is like finding a small, rural village that somehow possesses the same number of towering, thousand-year-old cathedrals as a sprawling capital city. Globular clusters are incredibly resilient, bound by their own intense gravity. They can survive processes that strip away diffuse gas and even individual stars. Their presence in Dragonfly 44 is a fossil record. It suggests that whatever this galaxy was in its youth, it was substantial enough to form or acquire a full suite of these stellar jewels. They are the crown of a ghost, hinting at a past richness that its current faintness desperately tries to conceal. Ultimately, whether it was born a ghost or made into one, Dragonfly 44 serves a higher purpose. It is a critical calibration point in our understanding of the cosmos. Our models of galaxy formation are built on relationships, particularly the connection between the mass of a galaxy's dark matter halo and the number of stars it produces. Most galaxies follow a rough rule. Dragonfly 44 shatters that rule. By studying it and others like it, astronomers are stress-testing the very framework of galaxy evolution. They are asking what processes can decouple dark matter from visible matter so completely. How efficient or inefficient can star formation truly be? These faint, dark matter-dominated ghosts are not mere curiosities. They are the extreme outliers that define the edges of the possible. They reveal the sheer dominance of the unseen, reminding us that what we perceive as a galaxy, the glittering spiral arms, the brilliant cores, is often just the faintest decoration on a form built from profound, invisible darkness. The profound darkness of a galaxy like Dragonfly 44 is a local mystery, but the oldest light in the universe holds a shadow of its own. Embedded in the faint, uniform glow of the cosmic microwave background, the afterglow of the Big Bang itself is a chilling anomaly. It is known simply as the cold spot, discovered by the Wilkinson microwave anisotropy probe in the early 2000s. This region of the sky is a vast circular patch that is noticeably colder than its surroundings. We are not talking about a dramatic chill. The difference is minuscule, about 70 microkelvins, or 0.00015 degrees colder than the average. But on a canvas of near-perfect uniformity, this subtle dip stands out like a bruise on the primordial sky. Its sheer size is what makes it truly bizarre. The cold spot spans an area of the sky roughly 1/10 the diameter of the full moon, which corresponds to a physical scale of over 1 billion light-years across if it originates from the early universe. In the standard model of cosmology, the cosmic microwave background is a snapshot of the infant cosmos. Its tiny temperature fluctuations the seeds from which all galaxies and clusters would eventually grow. These fluctuations are expected to follow a specific statistical pattern, like the gentle, random texture of ocean foam. The cold spot is not gentle. It is a large, deep, and coherent depression that, according to probability, should be exceedingly rare. In fact, some analyses suggest the odds of such a feature appearing by random chance in our standard model are less than 1 in 200. This forces a critical question. Is this just a 1 in 200 cosmic lottery ticket that we happen to draw, a simple statistical fluke in the data? Or is it a genuine crack in our understanding, a signpost to something fundamentally missing from our story of creation? The anomaly's persistence, confirmed by later observations from the Planck satellite, means scientists cannot simply ignore it. Its existence has sparked a search for explanations that venture to the very edge of cosmology, proposing structures or phenomena so immense they defy easy comprehension. The leading explanation for that billion light-year bruise is a cosmic emptiness. Astronomers call it the supervoid hypothesis. As the ancient photons of the cosmic microwave background travel toward us for over 13 billion years, their journey is not through a perfectly smooth universe. They pass through the evolving cosmic web of clusters and voids. When a photon enters a vast underdense region, a void, it must climb out of a gravitational well. Since the universe's expansion has accelerated due to dark energy, the well actually becomes shallower as the photon is inside it. This means the photon loses more energy climbing out than it gained falling in. This energy loss, known as the integrated Sachs-Wolf effect, manifests as a slight cooling of the microwave background in that direction. So, a truly colossal void between us and the cold spot could, in theory, paint that cold patch on the sky. The hunt was on. Surveys of galaxies in the cold spot's direction did indeed find a large underdense region, sometimes called the Eridanus supervoid. But here lies the tension. This void, while significant, may not be big enough or empty enough to account for the full depth and scale of the temperature drop we observe. It is like finding a small hill when your calculations demand a mountain to explain the shadow. This mismatch is the core of the ongoing debate. Some scientists argue that the void's contribution, combined with a dose of cosmic chance, a random, unlucky alignment of smaller fluctuations, could still explain the cold spot without new physics. Others see the insufficiency as a glaring clue that something far stranger is at work. This opens the door to possibilities that sound like pure science fiction. One extraordinary idea is that the cold spot is a bruise from a collision with another universe. In the theory of eternal inflation, our universe is one bubble in a vast, frothing multiverse. If, during its hyper-expansion phase, our bubble universe grazed another, the energy released at the boundary could have imprinted a specific, circular signature on the cosmic microwave background, a signature that looks exactly like a large, anomalously cold spot. It would be a fossilized scar from a contact with a reality we can never otherwise access. An equally exotic but distinct proposal involves cosmic texture. In the searing heat of the universe's first moments, as fundamental forces separated from one unified superforce, the fabric of space-time itself could have crystallized with defects similar to cracks forming in ice. One type of defect is a texture, a tangled knot of energy in the fields that govern reality. If such a texture existed and later unraveled, it would have released a spherical shockwave of gravitational energy that would leave a specific, circular cold imprint on the cosmic microwave background. A texture is not an object in space, but a kink in the very fields of space, and its dissolution would be a one-time event, leaving behind a unique fossil. Both the colliding universe and the cosmic texture ideas are profoundly speculative, pushing at the very limits of testable cosmology, yet their mere consideration highlights the depth of the puzzle. The cold spot is not just a data point, it is a stress test for our entire cosmic narrative. It asks whether we are simply unlucky in our observations, or breathtakingly lucky to have glimpsed evidence of a multiverse or a flaw in the primordial vacuum. For now, this ancient chill on the map of creation remains, a silent and immense question mark written in the faintest light of all. The ancient chill of the cold spot speaks of structures on a scale we can barely conceive, but sometimes the universe hides its most spectacular shadows around a single, familiar point of light. In the crowded central bulge of our Milky Way, a giant star catalogued as VVVWIT08 performed a disappearing act that redefined extreme. Over the course of 200 days in 2021, this star, observed by the VISTA telescope in Chile, did not just dim. It nearly vanished, its light dropping by a staggering 97%. For more than half a year, it hovered at a mere 3% of its normal brightness, a faint ember in the galactic core, before slowly, agonizingly returning to full strength. This was not a brief flicker. It was a sustained cosmic blackout, an eclipse of unprecedented depth and duration for a star not caught in the chaotic nursery of a young cluster. The star itself is likely an older red giant, a sun in its later years. This single fact immediately ruled out the protoplanetary disk explanations used for younger Dipper stars. A star this advanced has long since cleared away the dusty debris of its birth. Its planetary system, if it has one, should be settled and mature. So what colossal, dark object could possibly drift in front of such a star and block its light for so long with such perfect efficiency? The forensic analysis of the light curve provided a precise blueprint of the culprit. The dip was not a fuzzy, gradual decline. It had an astonishingly flat bottom, meaning for those 200 days, the obscuration was total and uniform. This tells astronomers the object blocking the light was not a fuzzy cloud of dust, but something with incredibly sharp, well-defined edges. Furthermore, the transitions into and out of the eclipse were remarkably symmetrical and steep. The best fit model, the one that matched this perfect geometric shadow, pointed to a single, breathtaking structure, an opaque, dusty disk. Picture a giant version of Saturn's rings, but on a scale that dwarfs our entire solar system, and so densely packed with fine dust that not a shred of starlight can pierce through. This disk would need to be millions of kilometers across, and we are seeing it almost perfectly edge on from our vantage point. As it orbits the star, it passes in front like a colossal, dark vinyl record sliding across a cosmic spotlight. The profound mystery is the origin of such a disk. It is far too large and dense to be a simple asteroid belt. The leading theory points to a cataclysmic event in the star's recent past on an astronomical timescale. Perhaps a gas giant planet orbiting at a great distance suffered a catastrophic collision with another giant body, or was torn apart by the star's gravity as it evolved. Such a violent disruption would have shattered the planet into a colossal cloud of debris. Over time, gravitational forces and collisions within that cloud would have ground the material down into fine dust and shepherded it into a flat, coherent ring, orbiting in the same plane as the original planet. Another possibility is the tidal destruction of a wandering comet swarm from a distant Oort cloud-like reservoir, though the sheer amount of material required makes a planetary-scale disaster more likely. VVVWIT08 shows us that stellar maturity does not guarantee serenity. Even an old giant star can harbor a recent history of absolute violence, its light periodically extinguished by the funeral shroud of a murdered world. This anomaly proves that the architecture of mature planetary systems can be far more dramatic and dusty than we ever assumed, with shadows cast not by forming planets, but by the magnificent, silent ruins of their destruction. The debris from that collision would not remain a chaotic cloud for long. In the relentless grip of gravity, the expanding field of shattered rock and vaporized ice would begin to organize itself. The countless fragments, all sharing the momentum of the original planetary orbit, would start to collide and grind against one another. Over time, perhaps just a few thousand years, this violent chaos would settle into a stately, flattened disk, a colossal ring of fine, opaque dust orbiting the star in the same plane as the lost world. This is the dark, sharp-edged occulter that drifted in front of VVVWIT08. Its 200-day-long eclipse is a crucial clue to its location. For an object to block our view for that many consecutive days, it must be both incredibly wide and orbiting at a great distance from the star. The geometry is inescapable. This dusty shroud is likely tracing an orbit far wider than Jupiter's path around our Sun, a lonely memorial in the cold outer reaches of that alien system. Yet, astronomers must consider every possibility, even if it means questioning the nature of the star itself. Could this be an intrinsic act, not an external shadow? Some rare types of variable stars, like our Coronary Borealis stars, are known to suddenly dim when they belch out vast clouds of sooty carbon dust. However, these dimming events are typically shorter, more irregular, and the stars themselves have very distinct chemical signatures. VVVWIT08 does not neatly fit that profile. The sheer duration and perfect flatness of its eclipse point more convincingly to a solid, orbiting structure than to a sporadic stellar cough. To settle the debate, scientists need to look with different eyes. If a warm, dusty disk is truly there, it should glow with a faint heat signature in the infrared spectrum. The next critical step is for telescopes like the James Webb Space Telescope to stare at this star and its surroundings, searching for that telltale infrared excess. Finding it would be the smoking gun, confirming we are witnessing not a stellar tantrum, but the funeral procession of a world. This single, profound blackout forces a dramatic shift in our perspective on planetary middle age. We often think of mature systems like our own as stable and settled, with planets tracing quiet, predictable paths for billions of years. VVVWIT08 screams that this is not always true. Cataclysm can strike at any time. A gravitational nudge from a passing star, the slow decay of an orbit, or simply bad luck in a crowded system can lead to a collision of titans. The aftermath is not just a flash in the dark, but a long-lasting monument of dust, a shadow that can fall across its sun for centuries. It reveals that the greatest eclipses we witness may not be from the birth of planets, but from their spectacular and ruinous deaths.